Hello again.
Thank you.
Welcome everyone. Welcome to the CAST International Symposium on Period of Automorphic Forms. This is Minhyong Choi from Posttech in Korea. It is my great honor and pleasure to host this exciting program with Professor Seok Shin from UC Berkeley. I'd like to express my special gratitude to our distinguished speakers, Professor Minhyong Kim, Professor Yiannis Sakellaridis, Professor Akshay Venkatesh, Professor David Benby, Professor Dohoon Choi, and Dr. Jeo Han. We mathematicians really enjoy gathering, visiting each other, talking, and writing things on the real blackboard. It was also a pleasure to have cookies or drinks during those meetings. Although it's not ideal as it in person, I'm sure that this virtual symposium will give us a wonderful opportunity to strengthen the international mathematical network among us, in particular, young ones. In addition to assessing, YouTube is free, so please enjoy talks. Before starting the first talk, we will have the welcoming remark from the President Han Min-gu of the Korean Academy of Science and Technology. He is the host of this symposium. Let us welcome the President Han Min-gu.
Should I say good evening or good morning to you? We are joining from the 4 different locations in 3 different countries for the 45th CAST International Symposium, and it may be difficult to decide which greetings I should use. Let me just say hello to every participant. I'm very much pleased to welcome you to the 45th CAST International Symposium entitled Periods of Automorphic Forms. Gauss, one of the greatest mathematicians, is said to have claimed mathematics is the queen of the science and number theory is the queen of mathematics. Number theory is not only one of the oldest branch of mathematics, but it is truly the heart of mathematics. On the basis, it is not surprising to learn that at least 2 out of 7 Millennium Prize problems are originated from number theory. I was also informed that major contributions, the 28 to 30% of 60 field medalists, came from number theoretical problems. The CAST International Symposium aims to provide a good opportunity to exchange valuable scientific achievement among renowned scientists from all over the world. It is unfortunate that we cannot afford to meet in a person due to the COVID-19. Of course, we may miss a glass of wine at the face-to-face symposium, but I'm still thankful that we can continue our academic journey. Today, my special gratitude goes to Professor Minhyong Choi for her superb effort in organizing today's symposium. And I would also like to extend my sincere appreciation to Professor Akshay Venkatesh, who is the 2018 field medalist, and other world-renowned speakers from Korea and abroad. We are also honored with the presence of great mathematicians from Korea, the United Kingdom, and the United States. I thank each of the speakers for sparing more time than on 1 hour, sharing your scholastic achievement in depth. I hope the symposium not only provide the exchange of research findings, but also strengthens the network among the participants for future collaboration. Let me now close by wishing you a delightful and a fruitful symposium. Thank you very much.
Thank you, President Han-Minggu, for a kind, encouraging, welcoming remark. Let us start. Professor Seok-Shin will be the chair of the talks. Professor Seok-Shin.
Okay, so let me introduce this symposium a little bit. So the main topic of this symposium is periods of automorphic forms. This classical theme lies at the crossroads of many areas of mathematics and beyond. Today and tomorrow, we will explore new development and ambitious future directions in this exciting and active area of research. And let me explain how this is going to work for the general audience. Thanks for watching this online. You can type in questions using the live chat on YouTube. The moderator, either Youngju or I, depending on the speaker, will interrupt the speaker from time to time and pass along the questions to get response. Your questions may be saved for the Q&A session at the end of the talk or saved for some other occasions due to the time constraint. Please be understanding. Now, our first speaker is Minhyong Kim, Christopher Zeman Professor of Algebra, Geometry, and Public Understanding of Mathematics at the University of Warwick. He got his bachelor's degree at Seoul National University and PhD at Yale before moving on to faculty positions at MIT, Columbia, University of Arizona, Purdue, the Korea Institute for Advanced Study, PostDoc, and University College London. Most recently, before moving to Warwick, he was research professor of number theory at Oxford and head of their number theory research group. He has also held visiting professorships at numerous institutions, including the University of Paris, University of Kyoto, Seoul National University, and the University of Toronto. In addition to papers on arithmetic geometry and its ramifications, he has published 5 books on mathematics for the general public. Now, was a long introduction. Now, finally, his title is Arithmetic Actions and Path Integrals, Some Examples and Challenges. Please welcome Professor Minhyong Kim. The mic is all yours.
Thank you very much. That was a very embarrassing introduction, but thank you nevertheless. So I guess I'll try to share my screen now. Can you see my slides? It's all right?
Yes.
Okay, and you can see my cursor as well, is that correct? When I move it around?
Yes.
Okay, great. Yes. To be honest, I don't know what I'm doing here because I don't know anything about automorphic forms or about periods, but the organizers clearly knew this when they invited me to give this talk. So if you don't like what I'm about to say, you should blame them, not me. In fact, it's going to be a very speculative talk. Some of you who have heard my talks in recent years will not be surprised by that. It's going to, there's very little of substance, but I'll try to make it somewhat entertaining anyways. So what I'm going to do, so here's a rough plan of the topics that will come up in the course of this lecture. I think I'll have enough time because Youngju very generously allotted me 90 minutes, I think, for this talk. In fact, it might go quite quickly depending on how gullible you are about what I'm about to say. But I thought I'd start today because somehow this whole, the theme that will follow all has to do with interaction between ideas from quantum field theory and arithmetic geometry, especially the hope that you may somehow use the quantum field theoretic notions in arithmetic geometry. So I thought I'd start with a very preliminary remarks, giving my view of what quantum field theory is about. Now that's a bit laughable given how little of an expert I am, my level of ignorance, but since I expect there are many number theorists listening who possibly even know less than I do. So for example, I spoke with Sagu about this topic last summer, and Sagu knows about more than me about almost every other topic under the sun, but I think he knows less about me, and less than me about quantum field theory in particular. So I thought about him as I was preparing this portion of the lecture. So as somebody who read chapter 2 while everybody else is reading chapter 1 as a student of the topic, I'll start out with this kind of a preliminary overview of what I understand of quantum field theory. So here's a very general remark, right? So what do physicists do as far as I'm concerned? Right? So physicists are concerned with mathematical models of physical systems. Right? A physical system can be anything in the universe. It might be the whole universe or a cup of water or the earth going around the sun. But typically, there are two parts to a physicist's model. Right? So they often model all possible states that the system can be in. Right? It would be good to give some examples, but I was too lazy to prepare. So for example, if you have just a single particle moving freely through space, then all possible states might be R3 cross R3, one for position and one for velocity, right? That's the kind of thing that physicists mean by the states of the system. I denoted it by S. Then another part of the model is a dynamical law that tells how the states change with time. Now, this is not exactly an accurate statement from a modern point of view, but it's reasonable enough that typically there are the states of the system, and the law will tell you how you should start from one state, the state to which it changes as time passes. So this is essentially what a physical model is, and you could, with very little exaggeration, you might say this is all that physics is about: modeling the possible states of a system, right, and giving a dynamical law. In classical physics, the set of states is usually a Poisson manifold, or sometimes even a symplectic manifold, and the dynamics, the way the system changes, is given by Hamilton's equation, or some kind of a principle of least action that's also called the Euler-Lagrange equations. Now, one talks about the physical theory describing all this. So this is something that's very confusing to people outside the area, but they'll talk about theories or space of theories and so forth, right? And in this context, it just refers to the choice of an action function, right? Essentially from the states to the real or complex numbers. And you choose this action function, and that's somehow supposed to be informed by your understanding of the physics and your intuition, right? But once you've chosen this function, then its Euler-Lagrange equation expressing the minima or extrema is supposed to tell you about the dynamics. So this set of all possible states that I denoted by S can be just thought of as the extrema inside some possibly larger space on which the action function is defined. What is this larger space? Actually, this larger space, there's some flexibility usually in choosing this. So for example, I'll give you an example of electromagnetism in a second, but you might be interested in all possible smooth vector fields. That might be S tilde, right? And though inside there, you might have some differential equation describing the ones that occur in nature. That would be S. So that's the typical picture you have of this inclusion. But there's usually some flexibility in the choice of S tilde. And how large you should allow the a priori possibilities before you constrain them to the physical states. How large you allow it to be you can choose. Sometimes there's interesting physics even in deciding that. So one should think of it as something like a flabby resolution of the actual physical states for people who do normal homological algebra. So for example, if you're interested in vector fields, if S is the set of vector fields that satisfy some differential equation, S tilde might be all smooth vector fields, or it might be all distributional vector fields. So it might be even larger than smooth vector fields. So the space you start from a priori before you narrow it down to the physical state has some flexibility in it, sort of like the flexibility in choosing an injective resolution of a complex. So that's roughly the flavor of this S tilde. Eventually, when you focus on this S as the possible classical states of the system, right, then S tilde is often thought of as quantum fluctuation of the classical states. That's a rather important interpretation that arises when all the dust settles around this theorizing. And a point of view like this is made very explicit in frameworks like BV quantizations of gauge theories. I'm just throwing around some terminology for people who know, who might be interested in looking into this afterwards. So this point of view, by the way, that S tilde should be like a flabby resolution of the physical state. This I first learned from Chae-seok Park, who's at Postech. And he really tried hard to convince me that this was the correct viewpoint. I'm really grateful that he did. Right. So when you talk about a field theory, a moment ago I talked about any physical system, it might be a particle or whatever, or a rigid body. But when you talk about a field theory, this S and S tilde are all some kind of function spaces on space or space-time. That's the nature of field theory. They're functions or vector fields or tensor fields or something like that, right? So you can regard S as being a space of functions on space or on space-time, where when you regard it as a function on space, you regard it as something like space of initial data for solutions to a differential equation that you foresee in the modeling. So as I said, for example, in electromagnetism, this is maybe the only concrete example I'll give for now. S tilde might be the space of pairs of vector fields, E and B, one for electric and another for magnetic on space-time, while S might be the subspace of vector fields just on space, right? Of all a subspace of all these pairs that satisfy these equations. This is in a vacuum, right? That is called Gauss's law and something, I forgot. Then the law of motion will be given by something like this. Maxwell's equation, dE dt is curl of B and dB dt is minus curl of B. I may have got the sign the other way around. I forgot to check that. But anyway, it's something like this. Right, so this is a typical example of what a field theory is like, what S might be like, and what S tilde might be like inside a field theory, right? And what the law of motion is like. This is Maxwell's equation, of course. Sometimes this point of view is maybe not so important to emphasize right now. Sometimes when you think about the space of all states, you might think about it in terms of the initial data or in terms of the actual solutions. These are somehow the same, given some existence and uniqueness of the differential equation you're interested in. So you can also think of S as being the space of fields on R3 cross R that satisfy all these equations. That's also a different way of conceptualizing all possible physical states. Philosophers actually make a big important distinction regard these two distinction between these two viewpoints, where one is just initial conditions, the other as actual solutions. They seem to regard that as very important, and they fight about such things actually. What is the more correct point of view? Whereas in mathematics, of course, it doesn't matter, mostly. Okay, but regarding this time evolution, in fact, a rather old-fashioned view will say that the time evolution of a field happens along space cross a small segment of time. Let's say if you're interested in how a field evolves from T0 to T1, you think about the evolving field as something living on n cross this interval. Right? But that's an old-fashioned view. Why do I say that? It's because these days, it seems to be much more important to consider something you might call a geometric field theory. Something that can be defined in an arbitrary Lorentz manifold, say, right? M, right? Four-dimensional Lorentz manifold, and with time evolution happening between one boundary and another. Right? So you think about one of the boundary as the state at one time, the other boundary as a state at another time, right? And the space-time interpolating between them can be very complicated. So this is a rather popular viewpoint these days, and people seem to regard it as rather essential to consider a field theory as living on arbitrary manifolds with boundary like this. The fact that the manifold, the space-time can have exotic topology is not such a strange fact at all. Everybody accepts these days, for example, that black holes exist in nature, so topology can't be so simple for space-time, right? But anyways, to be considering arbitrary manifolds like this as a domain that you need to consider to formulate field theory probably is a slightly radical viewpoint from the point of view of, say, mid-20th century physics. Why do they do that? There might be a number of reasons, but I'll give you one reason that physicists tell me is correct. I checked this with my friends. So, for example, one reason that they do this is because somehow they always, people who take this viewpoint of geometric field theory, they always do somewhat have quantum gravity somewhere in mind. So what does this mean in practice? What it means is that even if there's one fixed space-time that seems to be the dominant and observable model of the universe, right? From a quantum viewpoint, this space-time will always fluctuate to nearby space-time. The nearby space-times can always contribute to the phenomena that we observe in the space-time that we seem to inhabit, right? So any field theory that's realistic also needs to make sense on all these other space-time, and you have to add contributions to the state of a field from this nearby space-time. So that means that any realistic field theory, a priori, should be defined on any space-time. So that's the rough idea of why they want to do this. So, but this is not a big deal, of course, for most mathematicians. So, for example, for Maxwell's equations that I wrote in terms of these curls and divergences and so forth in classical coordinates, we all know that it's possible to formulate them in invariant way on arbitrary Lorentz or Riemannian manifolds. So we are quite used to this, but it's just that this is now seems to be quite mainstream among physicists as well. It's not an exotic thing to consider these kind of invariant versions of field equations on arbitrary spacetime, and also actions like this, like the one on the bottom. So this is an action that makes sense on any four-dimensional spacetime, Riemannian or Lorentz, and its Euler-Lagrange equation are given by these two equations above. Okay, so why am I discussing all this? So it's because I do want to mention that the algebraic structure, of course, I'm mostly interested in the algebraic structures that arise from this. And the previous slides, I don't really know what I'm talking about, but still, I wanted to give a rough idea of the science from which this inspiration comes. So far I've spoken about the classical fields. In quantum theory, so what happens? Well, people say that all possible states form a vector space rather than a Poisson manifold or a symplectic manifold. So how should one, where is this vector space supposed to come from? It is not incorrect to think of it roughly as something like the vector space generated by the classical fields. That is actually the way a lot of physicists think about a quantum state, as a kind of quantum linear combination of classical states. If you want to do it more rigorously, you might think about something like L2 holomorphic functions on the space of classical states. In order to make sense of it, of course, you need a complex structure on the classical space as well. So that requires more structure. But roughly speaking, if you think about it as L2 holomorphic functions that assign amplitudes to every possible classical state, right? That's a pretty close to rigorous version of what a quantum state is supposed to be. And in that sense as well, better than this vector space, it gives you a sense in which quantum states are superpositions of classical states. This is an incorrect viewpoint, by the way, but it is an intuitive view that physicists themselves use quite a lot. So this is why it forms a vector space, because somehow you're supposed to be able to take complex linear combination of states, even classical states.
May I interrupt for a second?
Oh, sure.
Yeah, the question is there a background moduli space of manifolds here? If we want to
sure. Yeah, of course. For the people interested in quantum gravity, yes, they are always having a moduli space of manifolds, including possible different topologies, but also if it's a fixed topology, different metrics, a moduli space of metrics, they always have that somewhere in mind, right? And what is an appropriate model of the space of metrics, even when you are doing kind of baby versions of quantum gravity, is something that physicists discuss quite seriously. Again, I'm not the person to ask about this, but I'm just giving the answer, as I said, of somebody who read chapter 2. Okay? Okay, yeah, thank you for the question. Right, anyways. So thinking of these possible states as being initial data in space, right? So if you have a field theory, right, what it does, it determines, say, a Riemannian three-manifold or vector space of the possible states of the field on that portion, on that space-like portion, space slice of space-time. Yeah. So this is one thing, now we're getting closer to algebra. Somehow, if you're doing this kind of field theory, it determines for every manifold, in this kind of geometric field theory, a vector space of possible states of the field on that manifold. Right? And then, if you have a four manifold with two boundaries like this, one of which there are various conventions for how to regard one as incoming and the other as outgoing, that four manifold will determine a linear transformation going from the states on the incoming manifold boundary to the states on the outgoing boundary, representing the way time evolution of the states of the field. So this is the algebraic structure that arises from this, and that mathematicians like me mostly focus on. From all that previous consideration, you end up having a situation where a three manifold has a vector space associated to it, and a four manifold with boundary determines a linear transformation. Well, this is supposed to be Schrödinger's equation, telling you how states of the field, quantum states of the field on the incoming manifold evolve into the ones on the outgoing manifold. Right. Now, so a little bit more algebra. It's not so, maybe it's not so important right now, but it's eventually quite important, but I will mention it. This assignment has the property of being rigid monoidal, that is, so maybe this rigid of the duality I won't explain so much, but this tensor product property is important, that it takes disjoint union of two manifolds. The states on there will be a tensor product of the states on one with the states on the other. The reason for this is also relatively clear. It's because if you consider a field on disjoint union of two manifolds, that's determined by a field on N1 and a field on N2. So it's just a product space of fields, oops, this should have been N1, sorry, SN1 cross SN2. The states of the field on N1 union N2 will be just a product of the states on N1 pairs and states on N2. Right? But then, because the quantum state is supposed to be like a vector space generated by such a thing, or L2 of such a thing, that naturally transforms this direct product to a tensor product. So that's why when you're doing quantum theory, the disjoint union of the quantum states of a field and disjoint union of manifold is just a tensor product of states on either component. And also, when you're doing this business, since now we're mathematicians, not physicists, so we have to consider somehow these extremal cases, right? So the empty set, for example, can be regarded as a n manifold for any dimension. So in this theory, the possible states of the field on the empty set just becomes the complex number C, right? And the morphism assigned to the empty four manifold, right, is just one going from C to C. So this all somehow follows from the previous property. If you follow through the axioms or the general known properties of this assignment carefully. But anyways, one important thing, therefore, is that when M is a four manifold without boundary, then this can be just regarded as a morphism from the empty set to the empty set, right? So the corresponding linear transformation just goes from C to C, so it can be regarded as a complex number. So this is the way you get assign the theory, the physical theory assigns a number to a manifold. Right? And I'm just doing this in 4 dimensions, but you can do this in any dimensions, right? As well, at least as far as the mathematics is concerned. Finally, as far as for this review, this is a pure review portion. A topological quantum field theory is a theory where the state space and time evolution only depend on the topology of the manifold. Right? It doesn't depend on metrics or anything like that. So that's the idea of a topological quantum field theory. Now, these things are quite curious objects. They became very popular starting in around 30 years ago, right? And have been studied extensively by both physicists and mathematicians, and is having an impact in many areas of mathematics for sure, but even in, say, something like condensed matter physics, something as realistic as that. But there are many consequences of the fact that time evolution only depends on topology. For example, the space of states that we discussed associated to a 3 manifold is necessarily finite dimensional in a topological theory. You can't have all these Hilbert space type of things for a topological theory. Also, if the boundary of a 4 manifold is empty, then this linear transformation, which we agreed is a number, right? This just will give you a numerical topological invariant of the manifold. So this is one of the reasons that topologists were interested in ways of coming up with theories like this, because these give you manifold invariants. So I only know this theory reasonably well in very low dimensions, 1, 2, and 3, right? And it gives rise to a lot of interesting algebraic structures, especially dimension 3. It's very closely related to theories of quantum groups, Drinford doubles of finite groups, and which all give rise to things called modular tensor categories. So these are the very best known algebraic structure arising out of three-dimensional quantum field theory. And these are things that are very interesting for mathematicians, I think. There are many reasons I think this is actually quite fundamental, besides the fact that they're just fun, is that somehow this idea that the topology of a space and fields living on it is related to this intricate algebraic structure. It raises to a new level, right? The kind of algebra/geometry that we learned after the time of Grothendieck, right? When we started learning scheme theory and associating spaces to rings and topoi and all these kind of things. So that's one way in which algebra and geometry became very intricately intertwined, right? And this seems to be another phenomenon of that sort, where there's algebraic structure which intrinsically have spaces built into them, and vice versa, spaces that reflect algebraic structure at a level that's somehow even more basic than when we were studying spectra of rings. It's a very interesting phenomena that's been happening over the last few decades, this interaction. I should also remark that these topological quantum field theory are not usually regarded as too realistic, right? Meaning they're not supposed to be. It's very rare that you'd have a realistic field, fundamental field that's a topological quantum field, realistic fundamental field theory that's a topological quantum field theory. But it is possible to start with a realistic theory, something that's close to a realistic theory, at least if you think supersymmetry is realistic, and take something like the cohomology of the theory, right, and get a topological theory. This is the most common way physicists build up topological quantum field theory. So I thought I'd just insert that as a remark, because that story is also quite interesting, but we can't quite get into that today. Right. But in general, a theory may depend on more data, as though, like electromagnetism that we discussed earlier. There might be fixed background field, like a metric or even a spin structure, or even an extra, some fixed vector bundle with connection that we used to build up theory of other fields, right? So in fact, one way of visualizing the situation is given a manifold, the relevant fields typically constitute something like an iterated fiber bundle. So depending on how many fields you are regarding as fixed. So there might be just pure topology. There might be a situation where you regard the metric as fixed, another situation where you regard metric and a spin structure as fixed, and so on, right? So there are different levels at which you can consider some things as fixed and other things as dynamics, whose variation we're studying, right? So at any given level, it's also possible to have a relative quantum field theory that, for example, gives you a function on F1, right? FM1, this first level, by simply quantizing the fibers of the further fields that you're throwing into your theorizing, right? I'll give you an example of this in a few minutes. One other remark, which is quite important, is that physically meaningful spaces of fields usually take the form these FM that you describe naively like spaces of vector fields, but also modeled out by some group action. That because sometimes when you're describing the field a priori, you're encoding some redundancy, and you get rid of that redundancy using a group action. So this is typical in gauge theories, theories where the fields are connections on bundles, right? And then these G's, we have these gauge transformations that get rid of the redundancy of description, right? So having to go to this quotient space is also a source of a lot of mathematical difficulty. Okay, finally, now, I keep saying finally, so maybe this isn't finally. Anyway, so the title of the talk has path integrals in it, so I'll now give you a very brief description of the simplest type of path integrals in some sense, right? So we said that if you have a field theory, right, this manifold, right, say a four manifold, for example, without boundary will just pick up a number, right? There will be a number that the field theory assigns to it. Okay? So how do physicists mostly think about that number? They think about it as an integral of some sort. What kind of an integral? Remember, there was an action that determines the theory. That's what I'm calling L. So you'll take something like e to the minus of the action, right? And integrate it over all possible fields, modulo these gauge transformation, these equivalence classes, right? Because these are the physically meaningful space of fields. You want to integrate over all such things, this e exponential of the action. So this is what's sometimes called the partition function. And this is the way physicists like to think about the number that you assign to the manifold. On the manifold, you consider all fields, modulo gauge transformations, right? And integrate over such a space. Of course, it's hard to imagine how you might carry out such an integral, and this is almost never well defined in a mathematical sense, but it's a source of a lot of inspiration and interesting ideas coming from physics for mathematicians as well. But in some sense, the applications of versions of this idea in geometry actually go back at least as far as the study of things like Donaldson invariant. Right? So when in the 1980s, when Donaldson was studying invariance of four manifolds, what did he do? He took a four manifold and considered the space of gauge fields on that manifold, right? And then topological invariance of the gauge field, space of gauge field gave you smooth invariance of the four manifold. So that was the first place where people somehow studying the space of all fields on a manifold told you something about the manifold, right? So it wasn't expressed in terms of a path integral. Witten afterwards expressed Donaldson theory in terms of these kind of path integrals, but some version of that idea certainly occurs in Donaldson theory as well, which then went through many different incarnations. So it's not such an unfamiliar thing to mathematicians. But now we'll move to what somehow the main topic of this lecture, right? Which is that this integral may not be a number, and it's for a number, but rather it's very often an element of a line rather than being your number, element of a one-dimensional vector space, even when you make sense of it in a physicist manner. And this can occur for a number of reasons. So it might occur because of some kind of a degeneracy in the action. I'll explain in a second. And also it might be because somehow when you try to do such an integral, even formally, right, there might be a lack of invariance of this exponential under the group of gauge transform. It might not actually pass to the equivalence relation. So something that becomes a number when you don't consider this equivalence relation, when you try to pass to the quotient space, may become simply an element of a line. That you need to fix some additional choice before you can turn it into a number. Let me give you an example, right? So here, this is an abstract example. I'll give you a concrete example in a second. So often actions for the physicists consider will look something like this. So phi is inside some vector space of functions, for example, right? And then the action might be an inner product, an integral, say, of some inner product of phi with a Laplacian type operator acting on phi. So that's a common form, right, that the action might take, this of a so-called free field, right? Then if you do an integral of this with respect to phi, that physicists often define this even when phi is infinite dimensional to be 1 over the determinant of delta. This is, of course, informed by the way we do Gaussian integrals in finite dimension. By the way, I was a little bit worried about this. Sometimes you see square roots and sometimes not. Here, when I do it for a complex field, not having the square root, I think is correct. So anyways, if D happens to be an invertible operator, then this is more or less a definition which in finite dimension you can prove as a theorem, right? In infinite dimension it becomes a definition. But if D is not invertible, then you can't quite turn this into a number. Of course, it wouldn't make sense because this would be, you get a 0 in the denominator, right? So, but even when it's not invertible, you can still define an element of a line, namely the determinant of cohomology of this operator. Take its kernel and co-kernel, right? And consider top exterior power wedged with suitable sign, right? And take the tensor product of that. Then it's still possible to define this integral as being an element of a line. But you need extra traces to assign a number. This is the kind of situation I had in mind. So this occurs often in physics. It can be even more interesting. There can be more structure. So for example, the action may depend on some additional parameter. Right? So if this is an operator, D is some operator, A might be some additional field like a connection, right? Then the whole action may be being depending on the parameter. Then this integral that we expressed a moment ago, for any fixed A in my line inside the line, and then as A varies, then it can be interpreted as a section of a line bundle on the parameter space. So this is another very common situation that arises in physics. So here's a very important example, and what the main one I had in mind. There's a situation where you have something called a twisted Dirac operators. You don't have to know the precise definition. It goes from some bundle of spinors, plus spinors to minus spinors in 4 dimensions, right? Depends on the dimension, but anyway, in 4 dimensions, it goes like that. And you can also tensor it with a vector bundle with connection. Then you get something called a twisted Dirac operator. Then if you do that integral a moment ago, when you just integral over these phi's are sometimes called spinors or twisted spinors in this situation. If you just do the integral over phi, you get 1 over the determinant of the Laplacian associated to this Dirac operator, right? But this, in general, will just be a section of a determinant line bundle on the space of this bundle with connection and the moduli space of E comma A, right? Rather than being a function. Otherwise, you'd like it to be a function, but it becomes a section of a line bundle. Then you need to figure out how to trivialize that line bundle to get numbers out of this through some additional structure or assumption. On the other hand, by the way, this is a situation, this is what I meant earlier when I was talking about this different levels of fields and how you can quantize relatively. A Dirac operator also depends on a spin structure and a metric, right? So you could allow the previous determinant to actually vary over all these moduli space, the space of these bundles with connections, space of metrics, and space of spin structures. You can do all of that at once. Of course, spin structure is a discrete space, but anyways, you can, there's all forms of space over which the determinant varies, right? And so this is an example of a situation where, for example, you can forget some of the structure. Then what does it mean to quantize the fibers? I mean, just do that funny path integral over the fields that you're forgetting in this arrow. So in the first arrow, you're just forgetting the phi, then you're integrating over just the phi, regarding the others as fixed. Then what you will end up with is a function on the space of these triples or a section of a line bundle. Or you can go all the way down to A and integrate over all the other things. Right? And then again, you get a function or a section of a line bundle on the space of A's. But as I said, this phenomenon where you fail to get a function but just a section of a line bundle is what physicists sometimes call an anomaly. So I'll say more about that later to the extent that I know, right? But among the people in the audience that I know about, of course, David Pensby knows infinitely more than I do, so I probably direct questions to him. Okay, so that's the physics background. So I'm sorry if that was boring to some people and so it sounded pretentious to others. The reason I wanted to speak about this is, in fact, there's an analogy that I've had somewhere in mind for quite a few years, but I was quite embarrassed to speak about it. And one effect of getting old is that you overcome this embarrassment and say, well, okay, I'll just say anything. Maybe it's useful to some people. Some people will make fun of me, but it can't be helped. So that's why I started out giving this somewhat lengthy introduction, right, to describe now the analogy that I've actually had in mind, right, reasonably honestly. Yeah. So in order to get to the analogy, now I'll make some preliminary remarks on arithmetic geometry. This, I'm sure, is pretty well known to most people in the audience, right? But maybe I'll present it from a point of view that isn't emphasized too often. It's also very well known, of course, but it's not emphasized too often. And possibly you'll already see analogy emerging, the analogy I have in mind emerging as I go through these slides. So what do you study in arithmetic geometry? So this is, again, a lightning review of arithmetic geometry, as I did with physics, just butchering all actual matters of depth and just giving a very broad sketch of what we do. But here, and maybe I'm a little bit more qualified than in the previous section to do this butchering. Anyways, what the basic objects are, we study arithmetic schemes and sheaves on them. So an arithmetic scheme is just a finite union of spectra of finitely generated rings like this, right? This is what a finitely generated ring is like, a quotient of a polynomial ring over Z. Sometimes you allow a little bit of infinite generation, like allowing Z to be Q or something like that. But roughly speaking, this is the main subject of arithmetic geometry, finite unions of this kind of spectra. Right? So this would include, say, varieties over finite fields or spectrum of the ring of integers in an algebraic number field and so on, right? The sheaves that most often studied is not just one kind. There are many kinds of sheaves, right? But most common kind is sheaves in the étale topology, right? Which is, well, what a number theory is mostly think about anyways when they talk about a sheaf. Now, there's also a notion of a motivic sheaf. Among these sheaves in the étale topology, you can consider those things that come from families of schemes parameterized by S. And that's also very central. They play a kind of central normalizing role whenever you study sheaves and family of sheaves. So we'll return to that later. But anyways, this is already, I think, on this slide. It's again, at the cost of some butchering, is a good summary of what we do in arithmetic geometry. We study these things. Exactly this collection of things. Sheaves are built up in some sense, but from locally constant sheaves, right? So, for example, if you consider derived category sheaves, they'll be generated by perverse sheaves, and perverse sheaves come from perverse extensions from locally constant sheaves and locally closed subschemes, right? So you can say sheaves are built up from locally constant sheaves. Locally constant sheaves in a tau realization, these correspond to representations of the fundamental group of X, right? So this is how representations of fundamental groups and study of sheaves are almost the same, well, not quite the same, but at least representations of fundamental groups are the building blocks. This as well includes the case where X is a variety over a finite field spectrum of a ring of integers or some number of primes removed from a ring of integers, right? In which case the space of such representation is exactly the Galois representations most commonly studied by, real experts in number theory, not like me, anyways, serious people. Now you might say the study, therefore, of these kind of sheaves, which are actually very mainstream objects in number theory, and their moduli spaces, whatever we mean by that, whether they are local deformation spaces or other rigid analytic spaces of characters or whatever, or pseudo characters, you can say that the study of sheaves and moduli spaces roughly corresponds to classical field theory, in the sense studied by physicists, the other kind of field, not algebraic number theory kind of field. So what I want to say is that there's also a quantum theory here, right? That's interesting to build up, right? Which sounds very fanciful. It is very fanciful. You're quite right to meet such a claim with skepticism, right? It's okay, because the skepticism is good for people making their ideas deeper and more relevant. So let me give you, within the context of the arithmetic geometry, a brief overview of L functions, which in my view is a kind of quantum version of arithmetic geometry, of the study of these moduli spaces. Well, what are L functions? These are exactly invariants of these pairs of an arithmetic scheme and a sheaf, right? So F here now, I'll be slightly more concrete. I'll regard it as a sheaf of A modules right, or a complex of sheaves where A is, say, some subring of C or a QP bar. But here I'll be slightly vague because the notion of a sheaf to discuss L functions properly should be flexible enough to include things like, say, compatible families of Mendelian representation, things that are not exactly sheaves in a simple-minded sense. But anyways, what is this L function? It's actually kind of an invariant. That's a better way of thinking about it. What it does, it assigns canonically to such a pair an element inside the dual of the determinant of cohomology of the sheaf. That's one way of thinking about L functions. It seems like a Baroque way, and not everybody thinks about it, but this is actually a quite natural way of thinking about the way we usually build up L functions. So this is the dual space of the determinant of cohomology. So let me explain this a little bit. So it'll become apparent what I'm talking about if I just tell you the conditions that this assignment is supposed to satisfy. Right? So what are the conditions? Well, the most important one is this multiplicativity. That's similar to this monoidal property of vector spaces and things like that associated that come up in the quantum field theory I mentioned earlier. Namely, if you're given an exact sequence, this is a linear version of a disjoint union, right, in some sense. Then then you'll get an isomorphism between the determinant cohomology of the thing in the middle and the determinant tensor product of the determinant of cohomology of the things on the side, right? Then the L invariant of the middle thing should map to the tensor product of the L invariant of the thing on either end. Right? So this is the basic multiplicativity. And in some sense, the way we actually think about L functions in concrete practice arises from this multiplicativity, at least formally. What do I mean by that? So for example, suppose you have a triple, a scheme, an arithmetic scheme, an open subscheme, and a complementary closed subscheme. Then you get an exact sequence of sheaves associated to that, so that the L invariant of the thing in the middle is a product. Well, there's a reason for this. You can put a tensor product in here or not, depending on whether you think of this as an element of a line or actual numbers. But anyways, I'll be very loose about that notation. So there's the previous condition for how we are supposed to assign this implies this kind of multiplicativity, right? So when we do this for Z, when we take Z to be a bunch of closed points and take the number of closed points to keep increasing, right, until we include all closed points, then formally, from that multiplicativity, we get that the L invariant of a scheme has to be a product of L invariants associated to its closed points, right? So that just follows from the multiplicativity. And there's also a normalization for finite fields. So if X is the spectrum of a finite field, then a sheaf is just a module with a Frobenius action. So in that case, you can compute cohomology from this exact sequence. 1 minus the Frobenius will act on the sheaf. The kernel will be H0, co-kernel will be H1. So you get an isomorphism from this exact sequence between the dual of the determinant of this guy tensored with the dual determinant of this other F, right? And the determinant of the things on either side, dual of that. Right? So you have to keep track of the sign a little bit, but this is the isomorphism you get. Well, but this thing here, between being a vector dual of a vector space and itself, there's also a canonical trivialization. This is a line, right? So there's a canonical element here corresponding, if you like, to the identity map or to the element 1 if you've trivialized it already. So there's a canonical element on the left side, so you get a canonical element on the right side from this exact sequence. So the normalization I'm talking about is that when you have a sheaf on a finite field, the L invariant should be just the element corresponding to this canonical identity element, right? Via this isomorphism. Okay. Now, what happens is that if the sheaf happens to be acyclic, so that there's no H0 and H1, if they're both 0, then there's another trivialization. The determinant of cohomology is just trivial. So in that case, if you do the calculation correctly, right, then the element that we just identified becomes like this. It can be identified with an actual unit of A. It becomes 1 over determinant of 1 minus Frobenius acting on an F. So this expression that we always see in L invariance just follows from the normalization. just described. And then for a general X, formally it should be a product over all closed points of this kind of, or the inverse of a determinant. So that's what I mean by that. So if you're able to assign such an L invariant to pairs of X and F, then this is what I mean by an L invariant. We can't do this a lot of the time, of course, because this expression may be nonsense, right? But that's what we would like to do in a theory of L functions, right? So there's also a kind of complex normalization, which says that if A happens to be a subring of C, and the natural infinite product, if it converges, right, that will happen, for example, if the sheaf has sufficiently negative weight, then in fact, this should be an actual equality. The assignment as formal equality should be an actual equality. So that's another normalization condition that we would like out of the theory of L function. There's also a p-adic normalization, right, that gives a kind of interpolation condition on motivic points of moduli spaces, right, leading to a compatibility condition with the complex L function that I'll say in a second. So there are three normalizations I've discussed: finite field, complex, and p-adic.
Sorry, Minhyong, could you clarify what the p-adic normalization, what extra data that is relative to the complex one?
Well, you know, if you have a moduli, so actually, I'll answer that. Can I answer that in 2 slides? It'll be better if I give a concrete answer and then return to general speculation. Okay? Yes. Thanks for the question. So now, as I said, we can't assign L invariants to schemes and sheaves in this way. We don't know how to do it. We can do it when you have sheaves of sufficiently negative weight, but in general, we can't do it. So the situation is that this is the subject of great conjectures of arithmetic geometry, right? Like the Hopkins conjecture or the main conjecture of Iwasawa theory, right? So in the complex situation, then you have the Hopkins conjecture, and in a p-adic situation, you have things like the main conjecture of Iwasawa theory, which roughly speaking, and this is easy to make precise, that for suitable moduli spaces of sheaves, right, then you can build up a determinant line bundle on these moduli spaces, right? And the conjectures propose that you can canonically construct non-vanishing analytic sections of such things, right, which are compatible with the conditions that we just stated. So the Hasse-Weil conjecture, for example, that the classical one will start with a motivic sheaf on the ring spectrum of integers minus a finite collection of points, for example, right? And then it will claim that you can assign an L invariant to these complex twists of the sheaf. You can twist the sheaf with these characters, right? And then that there should be an analytic assignment satisfying all the previous conditions, right, to a sheaf of this sort. So this is the Hasse-Weil conjecture, that you can always do this in such a way that it becomes an analytic function, right? Then the Iwasawa main conjecture says something similar. You could start with a motivic sheaf, and then typically in the simple versions, anyways, you consider twists by p-adic powers of cyclotomic characters, right? And it will say that you can define a p-adic analytic section of corresponding to this complex analytic family of Galois representations or sheaves. Now, in either case, when we take integer powers, either of this character, this complex character or the cyclotomic character, then these are also motivic, right? And then these become L invariants of motivic sheaves. And the compatibility roughly says something like this, that if we take these L invariants of these motivic sheaves and divide by some complex period, these are very precisely defined things, of course, at least conjecturally, you know, these situations, then this should be equal to the p-adic value invariant divided by a p-adic period. They should be able to divide both out in a canonical way to get algebraic numbers that you can compare, right? And they should be equal. So this is the compatibility between the complex and the p-adic side. And that's what I meant by so this thing I said earlier. The p-adic normalization typically uses the complex normalization and so builds up the p-adic family so that these motivic points are dense inside there. Right? And so that this normalization condition given by the comparison with the complex values nails down a unique section if it exists. Okay? Right. Okay, so that was a lightning review from the theory of L functions from the point of view of these determinants. Right. So now I'll move on to a slightly precise discussion of the analogies I have in mind. But actually, maybe I should pause for some questions here.
So I guess the most familiar setting is when A is Q or some number field, perhaps. But I mean, do you also propose some L functions formalism over, say, complex numbers?
No. This is just for arithmetic schemes. Remember, this X and F are just X is an arithmetic scheme and F is a sheaf.
Oh, I see. So everything is finite type over Z.
Everything is finite type. That's right. No, thank you. Although, by the way, actually, on the other hand, I do think such a formalism does exist in geometric Langlands. I have some vague ideas about it, but I don't know exactly how to make it precise. If you formulate things correctly as an assignment of a suitable sort like this, it should be possible in geometric Langlands over C.
I mean, there's also a good comment from YouTube that it's by Jace Getz. Is it known how to define determinant?
This determinants of cohomology? Yes, this is very well known. I mean, there are people who know better than I do, but yeah, so it's defined in a good deal of generality for lots of moduli space of shapes. I won't be able to give you a citation right now, right? But it's good to look at, for example, this old paper of Fukaya and Kato, right? But then there were later paper by, I guess, people like J. Potthurst wrote about these determinants, David Hansen, and a lot of people who work on these deformation spaces. So in a lot of situations where moduli of Galois representation is defined, people have defined determinant of cohomology line bundles. But I can't give you a precise reference right now.
Okay, I mean, yeah, just to pass on the message, Jace clarified that it was meant for arithmetic schemes, but yeah.
Say again?
The question is for arithmetic schemes. I mean, determinant for arithmetic schemes.
Okay. You mean as versus Galois representation? Okay. Yeah. You're right. Of course. No. Thanks for thanks to Jace for that comment. The case I had in mind was mostly when the scheme is just spec OF minus a finite collection of points. But actually, I think the construction shouldn't be that different for arithmetic schemes because. A lot of the things that go into construction of, say, for example, the spaces of pseudo characters constructed by Chenevier or more recent derived versions of this, they only depend on having a profinite group satisfying some finiteness conditions on their cohomology, right? So I don't think there should be that much difficulty in either building up the moduli spaces or the determinant of cohomology, even for arithmetic schemes. But of course, the devil is in the detail with any such construction, so nobody should take my glib answer as something actually knowledgeable. There might be, seeing as Jace is in the audience, there must be people in the audience more knowledgeable than me, so maybe they can also comment on YouTube.
Thank you.
Yeah, thank you. Okay, gosh, the time went more quickly than I thought. So I'll have to move to the analogies rather quickly. So there's this very old analogy that's become known as arithmetic topology. It's a very curious name for this series of speculations, but it seems to have stuck, so I'll use it. And it's supposed to go back to Mazur and Mumford in the 1960s, and many other people contributed, Morishita especially. Anyways, so in this idea, in this analogy, an arithmetic scheme like spectrum of a ring of integers is supposed to be like a three-manifold. This is for cohomological reasons that maybe I'll review if I have time in a few slides. And you have spectrum of one of these residue rings, which therefore becomes a finite field. Included inside spectrum of this ring of integers is thought to be similar to a not included inside the three-manifold. Of course, the spectrum of a finite field being like S1 is well known because its fundamental group is Z hat. Right? So it's like a KZ hat 1. If you remove this collection of primes, right, a finite collection of primes, right, then that's like removing a bunch of knots from a three-manifold. But you also can think of removing not just a knot, but a little tubular neighborhood, of thicken up the knots a little bit and remove a tubular neighborhood. Then you get a here it says sphere, I meant three-manifold, which boundary, and things that are like boundary tori, one for each of the primes, right, because you're removing these thickened knots. So that's the analogy for spectrum of these B integers. Right? And then, of course, fundamental group of these spaces should be like pi1 of three manifolds with boundary, whereas the fundamental group of the local fields, right, at the places you've removed. Right? So that's, remember, if this spectrum of OF mod P is like a circle, right, spectrum of OF completed at P should be like the tubular neighborhood. So that's an old idea, right, in algebraic geometry, not just in this arithmetic topology. But then when you invert the prime itself, it's like removing the central circle out of a solid torus, right? So you get something that's homotopic to a torus itself. So this spec of FV is like this tori, homotopically like tori, and its pi1 should be like pi1 of the boundary components of the three manifold. So this is the old arithmetic topology analogy, which I think is fairly well known now. So this also, the next thing is should also be well known, but I sometimes feel like I've somewhat popularized this idea that it's a really self-centered view. But anyways, that there's a way in which it's better to look at the dual of this analogy, right? Rather than focusing on the schemes and the primes, right? It seems the analogy seems to be better if you focus on representation, right? And their moduli. Because spaces of representations actually are much more similar to spaces of principal bundles on manifolds, right, than the schemes themselves. Even if we say a spectrum of a ring of integers is like a three manifold, it's nothing like a three manifold in any literal sense, right? But spaces of Galois representations are actually very much like spaces of principal bundles. That's just non-Archimedean version, right? So this makes the analogy much better to focus on this dual viewpoint. So, but then, now returning to somewhat the beginning of the lecture, if we regard this as being like classical fields, right, then it should be, this analogy should suggest that we can construct functions or sections of line bundles on these kind of spaces, similar to the physicist field theory, right? So that's one thing that's suggested by this dual viewpoint. So we should try to construct functions, things like action functions, right, on these spaces. To some extent, this is also very well known in number theory. So, for example, if you're given a knot in a three manifold, right, and you have a representation of a compact Lie group, G, right, then you get a function on principal G bundles with connection out of this knot and the representation sigma. How? You take a principal bundle with connection, restrict it to a knot, and take its holonomy around the knot, which will be an element of G, and then you can take the trace of the corresponding matrix in the representation. So you get a function of principal bundles once you fix a knot and a representation. So these things by physicists are called Wilson line operators. These are functions on spaces of these principal quantities with connections are regarded as the fields in this story, right? And the knot is regarded as giving a function there, right? Of course, number theorists know this very well. If you fix a prime, right, then a representation of, say, the target group of your some finite dimensional representation of the target group of your Galois representation, right? Then you get a function by simply considering traces of Frobenius. Right? So this is again very, very well known, right? But still, maybe for number theories, we're not so used to the view that you should regard the prime thereby as giving a function of representation. It does, of course, it's a triviality, but the viewpoint still seems to be nicely useful to think about this as a function of representation. Now, for people who are a bit rather knowledgeable, I'm going to just insert here 2 questions in the course of this analogy, just to say something that has slightly more depth than these completely well-known things. For those of you who don't know the terminology, you can tune out a little bit, right? So in topological quantum field theory, these Wilson lines actually form a category. So it's very natural to ask if primes with finite dimensional representations of the target groups attached to it actually form a category. And I do have some ideas about this, but for now I'll just state it as a question. Also, in TQFT, people discuss these things called Toft operators, not just Wilson line operators, right? And I'm not going to tell you exactly what it is, but I will tell you that the analogy suggests some very interesting number theoretic computations to do. Namely, what you should do is, if you can cook up these actions of Galois representation, you should consider integrals over all representations of this exponential. What kind of representations? You should integrate over Galois representations that are ramified with a fixed monodromy at some fixed prime. So these kind of things, this kind of computation is suggested by what physicists call Toft operators. As I said, I'm just mentioning it. It's fine if you've never heard of it, but it is a small indication of how new computations are suggested by the analogy with physics. In this case, of the computation of, say, some kind of a summation over ramified Galois representations with some fixed ramification type. So that sounds kind of natural, and that's exactly what physicists call Toft operators in quantum field theory.
So could you elaborate on the second question? What do we want to? Do we just want to compute this value, or do we want to compare that with something else? Or
yeah, so so I don't want to go into that because this is all very speculative, but yeah, so computation itself should be interesting. That's one thing, of course, yeah, that's what I'm claiming. But physicists will also say that this kind of computation is in some sense dual to the Wilson line computation. So in this geometric Langlands, this Toft operator is what become Hecke operators. The Wilson line operators are what am I trying to say? Yeah, Wilson lines correspond to Frobenius, right? And the Toft operators correspond to Hecke operators. I don't completely understand that statement too well myself, but people who like the Kapustin in the Kapustin-Wittgenstein story, they claim that it's only when they understood Toft operators, it only when they formulated it in terms of Toft operators that they understood what Hecke operators were about. That is the way they phrase it in their paper. Yeah. So they're somehow very central to the geometric Langlands story, this Toft operator. So there should be some kind of a duality between this kind of computation and integral over unramified representations. So that's vague, but I'm reasonably certain there's interesting computations. Okay, now as we're on this analogy, now since I asked 2 small questions, so I'll ask a somewhat serious question, right, in the vein of this analogy. Is simply so what we described just now are all kind of global local functions in some sense. So what about global functions? As I said, with the quantum field theory analogy should suggest that there should be things like action functions and moduli spaces of Galois representations, right? And so one difficult answer that I'm trying to give, or so we're trying to suggest in the previous slide, is that L functions themselves should be like these global functions. Well, that should be very difficult, but we don't know how to define them, of course, right? But there should also be easier answers. Functions of Chern-Simons type, BF type, these are all kind of physics jargon regarding different kind of action functions that arise in field theory, physicist field theory, not our field theory. But anyways, there should also be easier global functions defined on Galois representations, right? Besides these difficult things like L functions. So what am I trying to do? So this is where I sort of try to come clean and be honest about what I'm thinking, the way I've been thinking about this analogy, right? Ridiculous as it may sound, is that what I'd like to do is construct functions that are on the one hand like physicists' path integrals, right? And on the other hand are also like L functions, but easier than L functions. So that's what I'd like to do. We construct things that are like arithmetic path integrals, imitating the constructions of physicists, but also have properties of L functions and possibly thereby approach L functions through easier constructions. That's what I'd like to do, get out of this theory if some fantastic wishful thinking works out. Okay, so let me give you just a few examples. I've given versions of this talk many times before. So, actually, let me give you a really kind of outlandish example first and then give you some other more concrete examples. Here's an outlandish example, which isn't a real example, but just give it's kind of a completely formal example, but just give you a sense of what one might do, the kind of thing one might try to make sense out of. Suppose you had a sheaf on an arithmetic scheme corresponding to a unitary representation of its fundamental group. One can construct such things, just go to a finite quotient of pi1, right? Take a unitary representation of that. Now, if you fix such a sheaf, what physicists would regard as kind of quantum states of the sections of such a sheaf, one model for it might be just a product of all the stocks. That's kind of like a quantum states of its sections. This is like what I was referring to as distributional fields when you're considering fields in the sense of physicists. It's like such a product of stocks. So then, on such a stock, you can consider a function like this. This is kind of stupid, but it does give rise to a formal computation that's interesting. So on the stock, you have this Frobenius acting, right? So you can look at the function that simply assigns to a vector the inner product between Vx and 1 minus Frobenius acting on Vx. Right? So this will be some complex inner product. So if you integrate that over all fields, all these quantum states, right? What would you get very formally? Well, formally, first, this is like a local Lagrangian which you then will integrate over your scheme. But then this integral will become a sum, right? A formal sum, so that the exponential breaks up as a formal product over x, right? But then you're also integrating formally over a product over the stocks. So the whole thing will then become an integral of this local integral at x, then which again, by this Gaussian philosophy, formally becomes 1 over the determinant of this Frobenius, right? So this is a completely formal computation that shows you one way in which you can recover an L function out of a path integral. Now, this computation, by the way, I haven't really considered it seriously, but I suspect you can make sense out of this computation for a variety over a finite field. But that already would be rather interesting. But anyways, this is, as I said, kind of a outlandish speculative example of how you might construct L function as a path integral. But of course, this wouldn't be particularly useful because it does. I mean, it's just reformulating something we already know. It wouldn't make this product particularly more convergent than what we already know. So it's just kind of a toy, give you a toy sense of the kind of formalism that might eventually be useful. So as some of you know, instead I've constructed more elementary examples of functions over the past few years. So there's something like this arithmetic Chern-Simons function. So yeah, maybe okay, I'll go over this very quickly, even though I'm starting to get worried about time. I still have 20 minutes according to our schedule, right? Is that right? Yeah, thank you. Okay, so how does this go? So here, I can only do this with finite coefficients still. I simply haven't thought hard enough to do this with more interesting coefficients. But anyways, suppose you take a totally complex number field, spectrum of a totally complex number field. Now, there's a well-known fact that the H3 et al. Cohomology with coefficients in GM is just Q mod Z. So this GM is like S1 coefficients that Chern-Simons theory says like, but anyways, you get Q mod Z as a kind of invariant map via an invariant map. So where is this H3 coming from? Just to give you a brief reminder of that. So the point is this, right? So if you take GM, there's this exact sequence GM on X itself, and GM pulled back and pushed forward from the generic point, and its quotient is given by a bunch of copies of Z given by valuation, right? That's supported at the closed point. So you get this exact sequence in the et al. Topology. So if you take the long exact sequence associated to this, right, then you get H2 of this thing mapping to H2 of all of these copies of Z sitting at closed points. But that's all Q mod Z. So this is from these local computations that you see in the theory in local class field theory. And then you'll get H3 of X itself with coefficients in GM, but this can be identified with this very well-known reciprocity sequence. That's where this H3 being Q mod Z comes from. You identify H3 with exactly the same co-kernel you get in the reciprocity sequence. So it comes from class field theory, in other words. And this H3 computation is more or less, I guess, what inspired Maser in the 1960s to think up this arithmetic topology analogy. So if you take a finite coefficient, torsion coefficient like mu n, similarly, you get Z mod n, which I'm writing as 1 over Z mod Z in this, following this Q mod Z convention. Right? So from there, you can consider H3 of pi 1 with coefficients in Z mod n. That maps to H3 of X with coefficients in Z mod n, which then maps to Z mod n via the invariant map. So this gives you a very simple way of constructing functions of Galois representations. How do you do it? Well, what you do is, okay, you fix a finite group in this case. I'm calling it R. Sorry, I forgot to put that notation in R. Fix some finite group R, right? And fix a 3 cocycle of R with coefficients in Z mod n. So this is just some finite group thing. It has nothing to do with arithmetic a priori, right? But you fix a 3 cocycle of a finite group. Then, using that, we can construct a map, a function on representation of pi 1 into R. So how do we do that? So this is very easy. Given a representation, you pull back this cocycle to a cocycle of pi 1, which then, via this invariant map, will give you an element of Z mod n or 1 over n Z mod z. So this is a simple construction of a function on a very simple moduli space of Galois representations. Of course, to do serious things, I'd like to allow all kinds of ramifications and take limits over n as well. But this is also, it's already a bit interesting. So just to give you a sense of what you can do with this is, by the way, so here's a simple example of that, a concrete example. You can take R itself to be Z mod n, right? So then Mx is just maps from the class group to Z mod n, right? And you can cook up a concrete 3 cocycle in this case by taking a cup product between alpha and a co-boundary of alpha, where alpha is just a class of the identity map, right? And the co-boundary takes that class to H2 using a Bockstein map from this extension exact sequence, right? So that's an easy way to cook up a 3 cocycle on this group, right? So if you construct the previous Chern-Simons function for that, all you are doing is you're just taking invariant of the representation itself, cut product D of the representation via the Box-Time map. Oh, sorry, here I called it delta, here I'm calling it Z, but anyway. So in this case already, but you can construct, therefore, the Chern-Simons invariant. It's, of course, it corresponds to that cycle. You have to fix the co-cycle first, but now you can run over a row and take exponential 2 pi I of this number, right? So these will all be roots of unity, therefore. So you get an exponential sum of some sort, summed over Galois representation. So this, of course, is a simple case of an arithmetic path integral, where we're summing over Galois representation. Is supposed to be like integrating over fields. But this is completely well-defined. It's nothing like what the physicists have to struggle with, right? We should do this computation in the case, in the example that I just gave, right? Where you have take R to be, say, Z mod P, right? Now, I'm also going to assume that this Box-Time map is an isomorphism, and I'll tell you in a moment how to relax that assumption, right? But this is already an interesting computation in the case where the Box-Time map is an isomorphism. If you do this sum, what you get, this is joint work with these people. What you get is this kind of thing. It's a square root of the P part of the class number, right? And there's a power of I here. Okay? And then you get the Legendre symbol applied to the determinant of D. Now, determinant, this D is going from H1 to H2, but H2 is actually the dual of H1 via an arithmetic duality theorem here. Oh, I forgot to say, I don't think I said this. Yeah, sorry. I have to assume that the field contains all p-th roots of unity. Oh, sorry, I forgot to say that. So in that case, arithmetic duality makes H2 the dual of H1. So this is going from vector space to its dual. And in that case, you can define a determinant well-defined modulo squares. So this Legendre symbol is well-defined. So that's what's meant here. So a funny determinant shows up in the computation. So obviously, I've defined this quantity in analogy to path integrals, but the computation, I hope it's okay if I speculate that it certainly does smell a little bit of L function, right? When you actually compute the value. It's the kind of thing that does come up when you take special values of L functions when you regard it as, so in other words, when you take L invariants in the sense that I discussed. So the proof is easy, so I'm not going to show it to you. But by the way, when D is not an isomorphism, you do get a number as well, but it's also it's more natural, and I can't quite explain this right now. But when D isn't an isomorphism, it becomes natural to interpret the answer as lying inside C star torsor obtained from a Z mod P torsor. There is a determinant of cohomology of coming from this map that you can construct out of this situation, right? And it becomes natural to view the answer as lying inside this determinant in this case. More generally, so here's a computation I haven't done except in some very simple cases, which is quite interesting, but still. So but there should be a general picture like this, which should lead to interesting formulas as well. So you can start with a p-adic Lie group that you might like to consider as the coefficients of your representations, right? Then consider the Lie group modulo p to the n. So then you'll get some finite group here and modulo p to the 2n. Then you again get Box-Time maps associated to this situation and can try to write down action functions, right? But you see, in this case, if you look at the fibers of this map, right, you can sum over just the fibers. This is a situation that's quite analogous to this relative quantization business that I mentioned in the physics review, right? And the answer should lie inside the determinant line bundle varying over this bottom moduli space. So this is just mostly speculative, but some interesting computations that we've done already, which I won't really show you today. So here are a few remarks about that computation. So firstly, this operator D in this extension, of course, it came from a Box-Time, right? But I do think it's more interesting to view this as coming from very simple deformation theory. It is, of course, right? You're deforming a set Z mod n representation to Z mod n squared representation, and the obstruction to doing that is giving you the D, right? So people often have wild speculations about differentiating over number fields. But we often miss the fact that there are very simple differentials over number fields when we consider the very deforming the coefficients rather than the number field itself, right? So it's interesting to try to build up actions using differentiation in this moduli sense, right? So that's a comment simply. And as I said, the p-adic version of these constructions seem to be very hard, so I haven't really been able to tackle it yet. And there are lots of challenges, which maybe I wanted to say more about, but in the interest of time, I'll just skip over. Maybe I will show you the next very quick example. This is arithmetic BF theory. So this is very easy. So for physicists, there's a theory with this name, which is also quite easy, and it's easy in our case as well. So the way it goes is that if you would take a scheme like the previous one, spectrum of some totally complex field, and take these two H1s. So this is a space of principal bundles for Z mod n and mu n, right? And then there's a function on H1 cross H1 with coefficients in Z mod n, where again, you're just taking cup product of D of one side with the other, right? And take the invariant. Right? So here, I'm brushing a lot of detail under the rug, but to make sense of this, you have to use flat cohomology, right? But once you decide to use flat cohomology, all of this works in a straightforward way. H3 flat with coefficients in mu n is again just isomorphic to Z mod n. That's what you're using here. So you get this BF function on this kind of simple moduli space of principal bundles for finite group schemes over X. So obviously, then we would also like to take a path integral, right? Sum over all these principal bundles of exponential of this section, right? So what do you get when you do that? So you get a piece of the class group, right? And then the units modulo n, right? And also the class group modulo n. So if you take n large enough, this left-hand side will be trivial, of course, right? So essentially, it becomes like units times class group, right? So as I said, this also is like the special value of an L function appearing as an arithmetic path integral. So I hope I'm giving you some sense of what I mean, that it would be, I'm trying to construct functions that have both natures, path integral nature and L function nature. There's a version of this for dual abelian varieties satisfying some technical conditions, and rather the neuron model of such things that you again consider principal bundles for in the flat topology. So maybe I'll skip over the details and just tell you can define a BF function for this as well, and consider a path integral, right? Some overall possibilities here. If you do that, then you get again Mordell-Weil group modulo n's on both sides and n torsion of a Tetras-Freilich group. Now you have to make a bunch of assumptions about the component groups of the neuron model. You have to assume that the Tetras-Freilich group is finite, of course, as well. But this is the kind of formula you get. Maybe I should mention finally as an arithmetic connection. Proofs of these statements are all very straightforward applications of arithmetic duality theorems. Anybody can do that once you've seen the statement. If A is self-dual, right? So that this BF just becomes a function on H1 of the Tate modulo of A and H1 of the Tate modulo of A. You can do this p-adically in this case. This is one situation where the p-adic function is easy to define. And you restrict it to the diagonal. Then this becomes exactly, remember, this becomes this row cup D row type of thing that I showed you earlier on with the simpler examples, right? You can define them for torsors for the Tate modulo of the neuron model of an abelian variety. That actually does work. Right? But if you compute this, it's quite interesting that, of course, I have to tell you what D is. The D is associated to this exact Iwasawa theoretic exact sequence. Right? But if you do that, this function becomes exactly the same. So this Chern-Simons function, or exact analog of the Chern-Simons function in this setting, becomes Nekovar's p-adic height, the cyclotomic p-adic height, defined on H1. Right? So if you restrict it to the image of the Mordell-Weil group, you'll get the p-adic height of points as Chern-Simons functions. Now, so if you were able to integrate over this space, which I haven't quite figured out how to do, what I'm seeing is that, hoping is that you should get something related to p-adic regulators, but that's partly speculative, but it's kind of tantalizing, right? To see this computation working out and correspondence to well-known quantities and so on. Okay, so finally, let me finish up by there was something about challenges mentioned in the title of the talk, right? So what are some challenges? I wanted to list rather extensively, but I knew I was going to run out of time, so I'll just mention a few. So firstly, of course, there's a challenge I already mentioned, that most of the constructions examples I've been computing only involved finite sums, right, rather than actual p-adic integrals, right? It would be interesting to consider real p-adic versions where you do p-adic integrals over p-adic spaces of Galois representations of interesting arithmetic action functions. How would one get such actions? So I'm speculating that if we think about deformation theory more carefully, right, then physics should inspire more interesting action functions defined on moduli space of Galois representations. Now, but finally, so here's the thing that I mentioned that these path integrals taking values in determinant lines are actually not good things from the point of view of physicists. They want numbers, so they want functions rather than sections of line bundles. So that's why these things are called anomalies, right? And there's this viewpoint that I guess Dan Fried has written a lot about, and which I was only vaguely aware about, but David Bensby really convinced me that this is a good thing to think about, right? That anomalies are themselves actually invertible field theory in one higher dimension. Right? So if spec OF is like a free manifold, there should be a four-dimensional theory, right, which somehow accounts for these anomalies. So these constructing sections of determinant lines should be like a relative field theory for us, a field theory that's one dimension higher up, right? And so you could ask what that theory is, and I think the other three speakers actually have some deep insight on this question that I hope to hear about. Finally, of course, now, why did I give that long introduction to the physics? I really would like, so this is what I was sort of ashamed to speak about before, but I would like this analogy with families of Dirac operators to be made more precise. So for example, even if you start with a motivic sheaf and tensor it with this complex character, right? This does bear lots of resemblance to family of twists, leading to a dependent line bundle type of construction. So it is really like twisting a Dirac operator in some way. Well, you can take that in many different ways. For example, the motivic sheaf is something that arises from geometry, whereas this twist is something that's just living on our space, right? This analytic object on our space. So it's like somehow twisting using an auxiliary bundle on our space, right? So it seems there should be ways to make this analogy more precise. But you see, but what's the point? I mean, maybe I should say, this determinant line bundle for physicists is an annoyance. You want to trivialize it. Well, L functions are supposed to trivialize it for number theorists as well. So that's an interesting analogy there for me anyways. But you could say that, well, so why are you so obsessed? What's so interesting about this determinant line bundle? Well, I think many people find these determinant line bundles kind of charming on their own ground. So I have to admit that I just find them interesting on their own. There are some personal reasons I'm interested in this as well, just having to do with my own education, because I started studying determinant line bundles when I was first studying arithmetic geometry in relation with Arachelov theory. Somehow these local index theorems were able to combine them with scheme theory in Arachelov theory, and then there's determinant line bundles were everywhere. So this was very interesting. Personally, I've been always kind of interested in it. But so here's what I find. So now the next part is the really outlandish speculation, right? But since I've been talking about wishful thinking anyways, I'll finish with a final wishful thought, right? Which is why am I so obsessed with this determinant line bundle? Well, what I'm saying, you see, is that the geometric obstruction, right, for defining path integrals, and the geometric obstructions or L functions are very similar in nature. What do I mean by the geometric obstruction? I'm referring to this fact that you don't get a number, but an element of a determinant line. So this is somehow very similar on the two sides, right? So I'm hoping that this is just a hint of a lot more structural similarities between the definition of path integrals and definition of L functions. In particular, this should be kind of a trivial issue, just giving us a hint of structural similarities, right? But if true wishful thinking works out, right, it would be the much more speculative hope is that the analogy can be extended to analytic obstructions. You see? Because the more serious obstruction is not this determinant line business, it's simply this analytic continuation. That's the Hasebe conjecture, or the main conjecture of Iwasawa's theory in the periodic case, right? That's the serious difficulty, right? And I'm thinking that if we understand the structural similarity, there might be also analogy between the analytic obstructions and techniques for overcoming that. But you see, physicists are actually very good at overcoming this analytic obstruction. They find all kinds of ways of turning these infinite path integrals into finite quantities. This is this business of regularization and renormalization that you hear a lot about. They have a slew of techniques and traditions at overcoming, getting finite answers out of path integrals. But in a sense, in number theory, we're in a better state than physicists. The goal is simultaneously more modest in some sense, but also this modest goal, we don't have to worry about interpretation. So that's what makes it better in some sense for number theorists. What do I mean? Well, you see, when physicists come up with these ways of defining path integrals, right, making sense of path integrals that are a priori infinite, then they have to somehow argue that this makes physical sense. They may have used some weird regularization techniques and said that sum over 1 plus 2 plus 3, etc. is equal to minus 1 over 12. But that doesn't, even if they're able to do the analytic construction there, the answer has to make physical sense, which it might not, right? But in number theory, we don't have to worry about that. If we find any analytic continuation of L function at all, that's a major achievement, right? So whatever techniques they're using, if it leads to ways of finite, making path integrals finite, the wishful thinking is that this could be useful for constructing L functions. Okay, well, thank you very much. So thank you for your indulgence, and I've already said too much.
Well, thank you very much for the wonderful talk. Well, so it's time for Q&A. So I welcome questions from other speakers, from the live audience on YouTube.
I don't know any answers, by the way, but you can ask.
Well,
well, if there are no questions, so would you like? I lost you a little bit when you were describing your results and the pairings in cohomology. If you feel like, would you like to go through some part of it a little more slowly and?
You mean like here?
Explain just one result, or yes. Yeah, around this slide, I lost you a little bit.
Ah, okay, yeah, sure. So this maybe was a situation.
Maybe even earlier, I think.
Okay, maybe just this one, right? So here we have, so I'm viewing these H1s as all kind of very simple moduli spaces of principal bundles, right? One for the constant group Z mod n, the other for the non-constant group mu n, in the flat topology. So these are finite flat groups, right? So if you take a product of this, there's a you can quite easily define a function on this moduli space, right? And how do you do it? You just take, again, the Box-Stein map on the first factor, right, which will go from H1 to H2, right? And you take the product with the second factor. Then you end up with a class in H3 of mu n in flat cohomology. And that turns out to be canonically isomorphic to Z mod n, or 1 over n Z mod Z. Right? So you get an easy Z mod n valued function on this moduli space. Right? So this is an example of an arithmetic action function of a very simple sort. So BF theory, so physicists, when physicists do it, typically what would you do? You take a, say, n manifold, and you would take two differential forms of linking complementary dimensions. So if you have an n manifold, you can take a k form and an n minus k minus 1 form, say, for example, right? They look at functions like this, where you take d of one, wedge with the other, and integrate over the manifold. Right? Now, having given that function, then they integrate over all differential forms. That's what physicists would do. So here we don't have to do anything so drastic. We can just take this function now and integrate over all pairs A comma B. So that's now our arithmetic path integral starting from this arithmetic function, right? So that's what I wrote down here, right? Exponentiate the action, except I've snuck the 2 pi I in here, which is different from what physicists would do, but anyways. So you have this exponential. Well, it's not so different because the I, it occurs in the Lorentz path integral anyways. But now, and you sum over all AB. So this is an arithmetic path integral, which is rather precisely analogous to the kind of path integral that physicists do, right? And when you do an integral like this, you find arithmetic invariance of the scheme, of the arithmetic scheme, of the ring of integers of a scheme. But I was arguing, I don't know how successfully, but that this is exactly the kind of thing that comes up as special values of L functions, of course. So somehow this makes it plausible that we are building quantities that are path integrals, but L invariant theoretic in nature. So that was one example. The other that I showed you was when you have dual abelian varieties, and you can similarly construct this BF type function on H1 of n torsion of these neuron models of such abelian varieties. Okay, so these are also principal bundles for finite group schemes. Okay. I made some assumptions on n necessary for these to be both finite group schemes, like finite flat group schemes. And so then you define the BF function in exactly the same way, using n squared to a n map on the neural model. If you do this sum, you get, again, this Mordell-Weil group times Tate-Shafarevich group type of answers. So, which again is L invariant theoretic in nature. Well, by the way, but I think these are probably well known in some other form, and I'm just giving a very complicated version of it, right? But I still think it's at least to my superficial knowledge, because I'm not an analytic number theorist, I don't look at these things at all carefully, right? But expression of these invariants as exponential sums also seems not to be too well known anyway. The variance of abelian varieties. So if in the self-dual case, as I said, this would be Mordell-Weil group mod n squared times the Tate-Shafarevich group. The fact that you can express it as an exponential sum itself seems to be rather interesting. And that's a kind of concrete thing that comes out of this analogy, considering such sums in analogy with path integrals in physics.
Thank you.
Sure. Thanks for your question.
Okay, here's another question from YouTube by Hanbin Kang. There are some results from Schulte about the geometrization of some p-adic arithmetic objects. Will these results be helpful for solving challenges you suggest?
Well, I don't know, but so it isn't exactly, well, This isn't my idea, but there's a topologist named Clark Barwick. So he has a very interesting idea where, for example, suppose you take something like the Fark-Fontaine curve, or Schulz's diamond version of it, right? So you can think of that as being like spec QP, right? In some sense. That's a kind of more fattened up geometric version of spec QP. Clark's idea is that this analogy with topological quantum field theory or conformal field theory becomes much better if you replace these sparse objects like spec QP by things like the Fark-Fontaine curve or the associated diamond. So it's possible. For example, I mean, what can one do? There's a well-known theory of chiral algebras on Riemann surfaces, right? And Clark is somewhat studying chiral algebras on these diamonds. What it lead to, I'm not sure, but I think it's very interesting.
Okay, so to leave some break time, maybe this will be the final question from Akshay Venkatesh. Well, he has some background noise, so he chatted in the question. So have you attempted to define Chern-Simons invariant for a curve over a finite field? Raises question of algebraicity of connection on conformal blocks.
I haven't attempted to define it, but I mean, I think the kind of Chern-Simon invariants I discussed today, they certainly will exist for curves over a finite field. There's no problem doing it. So, but even there, if you wanted a p-adic version of it, it would be rather hard. But so attempts to define p-adic version of it was done by George Papas. So he has a paper, I guess it's only on the archive where he tries to do this. And it's hard for me to summarize the results in any straightforward way, but some version of it was done. This kind of finite thing is very easy, but George goes further than that as well. But I didn't quite understand the last comment. What was it about conformal blocks?
Oh,
okay, I'll risk the noise from my children.
Sure.
So if we have you could imagine you would like to define this as some kind of trace of Frobenius acting on the space of conformal blocks. And if the connection on conformal blocks is close enough to algebraic, you could imagine making sense of that.
I still don't think I quite understand. Okay, so you can have a curve over a finite field, and it probably makes sense to discuss conformal flock blocks on, say, for example, moduli spaces of curves over finite fields. Is this what you have in mind?
Well, maybe we can continue chatting offline since I think Sugwoo wants to preserve our break.
No, I'd love to hear what you have in mind.
okay, then, well, I'd like to thank Minhyong Kim one more time for his excellent talk.
Yeah, thank you. Sorry there were no periods, but
we're scheduled to resume in 2 minutes, but maybe everyone can take a very quick break.
Minhyong, I'll send you an email.
Oh, sure. Yeah. Thanks very much. Yeah.
Minhyong, wonderful talk.
Thank you. It's a bunch of load of nonsense, but what can I do?
guess it's time.
So should I?
Okay, welcome back. I'm very pleased to introduce Professor Yiannis Sakellaridis from Johns Hopkins University. He's a professor at Johns Hopkins, having previously taught at Rutgers and the National Technical University of Athens. His research interests are in the fields of automorphic forms, number theory, and repetition theory. And the title of his talk is Hamiltonian Spaces and Periods of Automorphic Forms. And all the floor is yours.
Thank you very much for the introduction. Can you hear me well? Yes. Can you hear me?
Yes.
Yes, okay. So it's a great honor to be invited to speak at this conference and to be speaking on the heels of this visionary talk by Minhyong Kim. My talk will be about ongoing joint work with David Ben-Zvi and Akshay Venkatesh, and therefore my goal will be to prepare the ground and formulate some questions that they will partially try to answer. So let me start. I actually have a second title image. So the first title image shows us connected, shows a connection, a virtual connection from the US to Seoul. I have a second version of this image, which is this, Americans trapped at home through their inability to control the virus while Koreans are enjoying their lives. So now let me get to math. I should say that it may be easier for people to have the slides available while listening. So the slides are available if you go to my website and just type cast PDF. So I will talk mostly about periods of automorphic forms today. So periods are a very old subject. Already Riemann used some kind of integral in order to prove the functional equation of the Riemann zeta function. So he considered the Mellin transform of a certain theta series. Mellin transform means the multiplicative Fourier transform. And a symmetry property of this theta series gives rise to the functional equation of the Riemann zeta function. So this is said in a classical language, but there's a modern, there's a different language to say this that was used in the theory of Iwasawa and Tate. So I'm going to adopt that language, the language of Adels. So I remind you that the Adels for the field Q are just a restricted product of all completions of Q, both the p-adic fields of p-adic numbers and the real numbers. And at first sight, what the Adels allow us to do is to write a simple sum in a complicated way. So that's the first thing that we will achieve with the Adels. So we will take a sum of some function, of some Schwarz function over the integers, and we will manage to write it in a much more complicated way. which is as a sum of a function on the adels over all the rational numbers. How does this work? Well, we take the function that we have on R and we multiply it with the characteristic function of ZP at every finite place P. And then if you write this sum, you just get the sum of the original function over all rationals who are integral everywhere, which is the same as the sum of the original function over the integers. So the adels allow us to write a simple sum in a complicated way. That's not much of an achievement, but they also allow us to change the lattice that we're summing over by changing the function that we're summing. So if instead of the characteristic function of ZR for a prime R, I use the characteristic function of R to the I times ZR, then this would change my arithmetic lattice from Z to R to the I times Z. So this is the language that we're using, and then you can take this sum of the theta series, here's the theta series again, and rewrite it as an adelic sum, and then you end up with a Iwasawa-Tate reformulation of Riemann's proof of the functional equation, which starts with a function phi on the adels, takes its theta series, which is just the sum over all rational numbers. So here F is the field of rational numbers, and then takes its Mellin transform against the character, any del class character. And that gives you the corresponding Hegel function. Of course, the left-hand side depends on the choice of test function, and the right-hand side does not depend. So everything, all these equalities that you will see in my talk will be for a suitable choice of test function. And eventually we will switch to function fields where there is a canonical choice at every place, and it is this choice, the characteristic function of the integers. And the critical local calculation here is that if you take the Mellin transform of this function, what you get is you just get a geometric series. You just get a sum over powers of the uniformizer, of positive powers of the uniformizer of this character, and this is equal to the L function at 0. So very soon we will focus on function fields. So instead of the rational numbers, we will be talking about the function field of a projective curve, a smooth projective curve C. So in that case, again, we have the adels as a restricted product over all completions at all points of C, at all closed points of C. And in that case, the quotient, so I forgot to stress that this theta series now is a function on idel classes, right? So it's a function on the idels, which is invariant under F star. And on the other hand, it is also, you can also take your test function like here. So you can take your test function to be invariant under the units at every place. And in that case, this quotient has a geometric interpretation as the Picard group of the curve. So actually, you see here the quotient on the right is the divisor group on the curve. And you divide the divisors by principal divisors, and you end up with a Picard group. And as a matter of notation, this quotient of adelic modulo F points, where F is our global field, will be denoted by brackets G in my slides. And sometimes I will be modding out by a good maximal compact subgroup, like the product over all places of OV points of the group. So for example, in this notation, brackets G modulo K is the Picard group of C, of the curve. So let's understand geometrically what Iwasawa-Tate theory means. if I choose, so we're still in the function field case, if I choose my test function to be the characteristic function of the integers at every place, the theta series that we wrote down before, just summation over, averaging over f star points, becomes a function on the Picard group, and it has the meaning, so the Picard group classifies line bundles on the curve, and the value of this function at the line bundle is the number of sections of this line bundle. Okay, so, and here's the explanation. If you represent a line bundle by a divisor, its sections can be identified with those meromorphic functions whose valuation multiplied by the divisor is greater or equal than 0 at every place. So this is the theme that we're going to consider today and try to generalize and to understand. We will be starting with building some theta series, and then considering their integrals against, well, Idel class characters or their generalizations, which are automorphic forms. And there's a whole universe of examples of this form, theta series paired with automorphic forms to produce L functions. But just since I will be using L functions, you will see some L functions in what follows. Let me clarify that I'm talking about automorphic L functions, so the L functions are associated to automorphic representations. Conjecturally, to every automorphic representation, you can attach something like a Galois representation into the Langlands dual group. So here I'm writing WF for the veil group in the function field case. In the number field case, the veil group is not exactly the correct object to consider. There's a conjectural extension of the veil group, sometimes referred to as the Langlands group of the field. Anyway, so let's think about them as Galois representations or homomorphisms from some version of the Galois group into the L group of G, the dual group of G. And when I say L function, I have to give you some extra data, and that extra data is is a finite dimensional representation of this L group. So if the automorphic representations corresponds to a Galois representation, and I compose this into the L group, and then I compose it with rho, I get local L functions that I can multiply. I can consider the Euler product, and this is the definition, ad hoc definition, but this is the official definition of the automorphic L function attached to the automorphic representation pi and the finite dimensional representation rho of the dual group. Moreover, the parameter S here is a red herring, and you can mostly ignore it because you can just incorporate it into this representation of the L group. So you can just change this representation of the L group by an absolute value of the veil group to the power S, and then you're really secretly talking about an L function at S, although for the new parameter, this is an L function at 0. So if in some slides you're missing the point of evaluation, just think of it as 0, but this could classically, depending on a twist like that, that would correspond to an L function at a different point, possibly. Okay, so now let me introduce some philosophy before I talk about other examples. So our philosophy is that in order to find integrals representing automorphic L functions, one should consider quantizations of suitable Hamiltonian G spaces M. So I will explain what this means, but just for a start, we are fixing a group G and we want to consider L functions for automorphic representations of G. And the philosophy is that one should start by considering suitable Hamiltonian spaces of G. So what does suitable mean? So first of all, for today's talk, this is very restrictive, and certainly this can be extended, but this will be an object of future work. So for today's work, for today's talk, M has to be smooth and affine. It's a smooth and affine variety with an action of the group G and a symplectic structure. So M is a symplectic manifold with an action of a symplectic variety with an action of the group G. And moreover, this action of G is Hamiltonian. So the infinitesimal action of the Lie algebra is induced by a moment map, by the Hamiltonian vector fields arising from the moment map. Basic examples of these are when M is a cotangent space, the cotangent space of another G space X, or when M is the symplectic representation of G, a vector space, in which case the moment map is a quadratic map. And very importantly, if we want to see L functions, M should have some multiplicity-free property in the universe of Hamiltonian spaces and in the theory of Hamiltonian spaces. This is called co-isotropic. It is a condition about the G invariant vector fields being Poisson commutative, the G invariant functions being Poisson commutative on the variety. Since probably many people in the audience do not have experience with this language, let me just say that this is morally saying that the spectrum of well, this is morally saying that if you consider G representations, you don't have, if you can associate G representations to this space, then you don't have multiplicity. This Poisson commutativity property is related to some statement like the endomorphism of some eigenspace is commutative, which will make it multiplicity free, something like that. Anyway, we'll get to specific examples. The basic example here is if M is the cotangent space of an affine G variety, then M is coisotropic or multiplicity free if and only if the variety itself is spherical, which means that its coordinate ring is a multiplicity-free sum of highest weight G modules. By the way, a lot of the things that I'm saying here require the fields to be of characteristic 0, and then we're going to apply this philosophy to fields of positive characteristic. That's okay, because at this point, this is just a philosophy. Yeah, so for these slides, maybe you should think of a field in characteristic 0. Okay, and then we have some technical properties. That's the last bullet that I don't want to insist on. Most importantly, the action of the group commutes with an action of the multiplicative group. That ensures, as you will see in a few slides, that ensures that the Hamiltonian space that we have is in some sense geometric. It's very close to being a cotangent bundle, although it's not necessarily a cotangent bundle. I will talk about this in a moment. And what do we mean by quantization of this space? So here I will mean something very, very precise. Well, no, not very precise, but it will, in examples, it will be precise. In general quantization, we will mean a local and a global quantization. Locally, what it means is that out of the space M, we want to produce a unitary representation, omega sub V, for every finite place, for every place of our field, for every completion of our field, a unitary representation of the group G of FV in such a way that somehow this unitary representation is a deformation of functions on the original symplectic space, namely functions on the original symplectic space should deform to operators on this unitary representation, and the Poisson bracket of functions deforms to the commutator of the operators. So we want to see a local unitary representation, and we want to see an automorphic realization globally of this tensor product of unitary representation. So we have now a unitary representation at every place, and we want to realize this tensor product of representations in the space of automorphic functions for our group. And here I wrote a restricted tensor product because, and this is very important, this local representation will come with a distinguished vector. So when I write tensor products, I will assume that at almost every place, I'm choosing this distinguished vector. So what are the basic examples of quantization? The first one is just suppose that M is a vector space, a symplectic vector space. Then the official quantization of this is the veil representation or the oscillator representation. And one can describe it through, for example, its Schrödinger model. So here I'm going to be ignoring many twists, metaplectic twists, half-density twists throughout the talk, just to keep things simple. So the Schrödinger model, if you choose a Lagrangian subspace inside of your vector space, identifies the Hilbert space of this representation with L2 of this Lagrangian subspace. And if this Lagrangian subspace happens to be invariant under the action of the group, then that's it. That's the whole story. That's the representation. If not, then you have to write complicated formulas for that involving Fourier transforms. And you have to pass to the metaplectic group, but I will generally ignore this. What is the global quantization here? The global quantization is also well known. It's the theta series. So in this Schrödinger model, you just take your function and you add it, you take its theta series again. You sum it over all the rational points of your Lagrangian, and then you start acting on your function, and that gives you an automorphic function.
Excuse me, Yiannis?
Yes, yes.
I mean, I presume you can't actually get the Poisson algebra of functions to act on this. So how much do you want to actually act?
Yeah, so I don't have an abstract answer to your question.
Mm.
Yes.
It's not really that important then.
It's not. It's not important. Yes.
Okay. Yeah. Thanks.
Yeah. So, and as you will see, the conditions that you're putting on our space allows us to declare that the quantization is always going to be obtained in very specific ways, and I don't think I can add something to the abstract question that you asked.
Sure.
So the second example is when M is the cotangent space of a G space, then its quantization will be declared to be L2 of that space locally. And again, globally, we can consider the theta series, which is just the summing again over all the rational points of over the discrete subset inside of the adelic space. Remember, so here we're taking adelic functions and we're summing over a discrete subset of our space, and that produces an automorphic function again. And the basic function throughout is going to be the characteristic function of the integers of our space. And actually, especially when we're over function fields, where we have the choice of making this, we have this basic function available at every place, then I will just drop it from the notation. And instead of writing theta series of phi, I will be writing theta series of m or theta series of x for this particular choice of test function. So what are the questions that one can ask about theta series? The first question is to evaluate the integral of this automorphic function against suitably chosen automorphic forms. That would be a direct generalization of Tate's thesis, where we had a theta series and we integrated against an ideal class character. So what will be the output of such an integral? And a closely related question is, instead of choosing an automorphic form, let's just take the theta series, project it to the space of a given automorphic representation, and calculate the L2 norm of it, of this projection. This is a slightly weaker question than the previous one, because it can be reformulated as saying that we want to calculate the sum of this theta series, the sum of pairings between the theta series and an orthonormal basis of our representation, absolute value square. So this is a slightly weaker question, but it has the benefit that it does not require you to choose a specific automorphic form. And calculating this pairing, these projections of the, so you just take the L2 norm of the theta series and then you calculate it through its projections to various automorphic representations. This is the object of study of the relative trace formula of Jacquet. And what does experience suggest? Experience suggests that under some conditions on the space that we're considering, like the conditions that I mentioned before, we expect both answers to be related to L values, spatial values of L functions. So the themes that are going to be explored in my talk and the following talks, first of all, I want to just give many examples of quantization and to convince you that many familiar constructions in the theory of automorphic forms are encoded in this concept. Secondly, I would like to talk about the Euler factorization principle that says that conjecturally, the answer to the questions in the previous slide is surprisingly related to the local unitary structure. So if you notice, the question in my previous slide had nothing to do with the local quantization. They were just questions about the global theta series and its pairings with automorphic forms. But surprisingly, there is an Euler factorization principle, at least conjecturally, which says that these global questions can be answered in terms of the local Plancherel formula. Then I'm going to pose questions about relations with L functions. You will see some answers in the talk by Akshay. And then I will try to formulate geometric versions of these questions. So this here is going to be the longest section in my talk. I will devote most of my talk on discussing examples. Again, the slides are available on my website at cast PDF if you get lost at some point. So the first class of examples is the linear paradigm when M is a symplectic G space. So here's an example generalizing Iwasawa-Tate theory. Godemain and Jacquet worked with a space of n by n matrices under the action of the group GLN cross GLN. So let's just blindly follow the recipe that we have been describing. we take a test function on the space of matrices. We act on it by the group. Here the group acts by left and right multiplication. And we consider its theta series. This is we consider its theta series, and then we integrate it against an automorphic form on our group. Because the group is a product, the automorphic form, I have written it as a product of two automorphic forms. Now, of course, these two automorphic forms have to be related, because this integral can be rewritten as an integral of the original test function on the space of matrices against a matrix coefficient. So in order for this to be non-zero, the two representations, the automorphic representation has to be of the form tau tensor with tau dual. It cannot be an arbitrary representation of G. And if you compute this integral, again, for a suitable choice of phi and f, or actually the story here is a little bit more complicated, but it's not so important. For a suitable choice of phi and f, if you compute this integral, you get the standard L function of the automorphic representation tau. And the point of evaluation here seems to be a little bit strange, but actually this is because we didn't normalize correctly. If you normalize correctly, you really shouldn't work with functions, but with half densities. So that means that you should multiply the function with the square root of the modular character, the square root of the character by which the group acts on a volume form. And then this strange point of evaluation gets corrected and becomes 1/2, the center of the critical strip. So that's one example of the linear paradigm. And in this example, X was n by n matrices, so M would be the cotangent space of X, but X itself is stable under the group. In the next example, again linear, but there will not be any Lagrangian stable under the group. This example is the example of Howe duality or theta correspondence, where our group is a product of two groups which are each other's commutator inside of a big symplectic group of a vector space. I will ignore metaplectic covers, but obviously I have to be working with metaplectic groups in many cases. So we have the veil or oscillator representation of the big metaplectic group. We choose a test function on it. We form its theta series like we described before, and now we integrate it against a pair of automorphic forms of G1 and G2. What do we get? The answer is given by the Rayleigh's inner product formula. So first of all, once again, we cannot take, so here I'm using giving an example in the case where G1 is an even orthogonal group and G2 is a symplectic group of the same, whose standard representation has the same dimension. So again, we cannot take an arbitrary representation of the product of these two groups, and that's actually the point of Howe duality. The point of Howe duality is that the restriction of this representation to this dual pair gives rise to a correspondence between representations of the two factors. So my representation should be of the form tau tensor with a unique representation of the group G2, depending on tau. And if I try to calculate the projection of the L2 norm of the projection of the theta series on the space of this representation, by the way, many simplifying assumptions in the background, this projection will make sense generally when pi is in the discrete spectrum or cuspidal. Okay, so all of these are assumptions that I'm just not mentioning. But then the Rayleigh-inner product formula says something very important, that if you calculate this global pairing, then it turns out to be an Euler product of local pairings. And the local pairings that I'm writing here should be the local pairings of this unitary representation at every place. So if you decompose, so you see here we have two a priori unrelated pairings that are bilinear in the argument phi1 and phi2. One of them is global and comes from automorphic forms. The other is completely local. But if we decompose the local representation according to its Plancherel formula, then we obtain the local factors of this global pairing. And the Plancherel measure here should be the standard Plancherel measure on the even orthogonal group, special orthogonal group. And moreover, the local factors at every place are L functions at 1/2 or at almost every place. Okay, so actually this product that I wrote has to be regularized, like in Minhyong's talk. It's really a partial L function at outside of a finite number of places times a product of finite factors. So this is what this is a reinterpretation of the Rayleigh's inner product formula. Another paradigm is the period paradigm. So now our Hamiltonian space will not be linear. It will be the cotangent space of a G space X. The G space X is GL2, and the group G is GL1 times GL1, acting by left and right multiplication. So I take an automorphic form on the group GL1 that consists of an Idel class character and an automorphic form on GL2. And the Hecke integral is the integral of this automorphic form on GL2 against this character against this Idel class character, and for suitable choices it gives you the L function, the standard L function at 1/2. A priori this doesn't look like a theta series, but actually it is a theta series. It is an integral against the theta series. So let me explain it in the case of function fields, where our cusp form is everywhere unramified. Then there's a canonical choice. Again, like we said, there's a canonical choice of, so here, I'm sorry, I should have rewritten it. I mentioned it in a previous slide. Our quantization in this case is L2 of x. So we need to choose vectors in L2 of x for every place. That's how we will form the theta series. And we have a canonical choice at every place. We just take the integers of the characteristic function of the integers. We form the theta series, and then it's a completely formal thing that the period integral that you saw before, the integral over the subgroup GM, is equal to the integral of the theta series against the automorphic form on the entire group. So in my experience, this can be a very confusing statement, but on the other hand, it's very, very straightforward and formal. So if you are not familiar with this equality, I would say just take it for granted that an integral against the theta series, when this theta series is on a homogeneous space, is roughly equivalent to an integral over the stabilizer of some point. Okay?
Yiannis, may I ask?
Yes. Yes, of course.
So we have seen that we can think of this L function for GL2 in two different ways, like Godemont-Jacquet and Hecke. So is there any way to see the connection directly, or are they just two different things?
So there is a fantastic paper or a couple of papers which appeared on the archive recently by a student of Joseph Bernstein who just graduated, Gal Dor. And he makes a very nice connection about, he just answers this question, and he also does other amazing things. So I really recommend looking at this. But I could explain what he does from the point of view of what I'm talking about today, but this would not be feasible within the context of this talk. So let me just say that for the purpose of today's talk, these two constructions are completely unrelated. And moreover, as you will see in a moment, the L functions are actually not the same. So let me actually make this point. It's this remark that I have here, that in the Godemaja-K case, we normalized our cusp form or our automorphic form to have norm 1. That's how we get the standard L function. We need to normalize so that the L2 norm of the cusp form is equal to 1. In the formula that you saw here in the Hecke case, a different normalization is presumed, and this normalization is that is the Whittaker normalization, that the Whittaker function, the Fourier transform, the first Fourier coefficient is 1. If you correct for this discrepancy and you actually use the L2 normalization for your cusp form, then you have, because we know that for Whittaker normalized automorphic forms, and again, I'm taking everywhere and ramified here over function fields. We know this formula for Whittaker normalized automorphic forms on GLN, and therefore if you correct for this discrepancy, the answer here would not be just this L function, but this L function divided by the square root of the adjoint L function at 1. So you actually don't get the same answer from the two constructions. Okay, and I would also like to mention the geometric interpretation of this integral, again, over function fields. So in this case, the automorphic space modulo a maximal compact subgroup can be identified with a set of pairs consisting of a line bundle on the curve and a rank 2 vector bundle on the curve. And the theta series just counts the number of morphisms from the line bundle to the vector bundle, sheaf morphisms. Okay, thought of as sheaves. So generalizing the construction of Hecke, Valspurze proved, and much later Gross and Prasad, and much later Gan, and a little bit later Gan, Gross, and Prasad formulated vast conjectural generalizations of these formulas of Hecke and Valspurze. And what do these formulas, these conjectures say? The conjectures here are not about the period itself, but the absolute value square of the period. And they say that for suitable automorphic forms, the absolute value square of the period is which period? We're talking here about the example of SON embedded diagonally in SON times SON plus 1. So SON will be denoted by H, the product of the two groups is G. We have a standard L function for the product of the two groups, okay, because it's just the tensor product of standard representations for the dual groups. And then the conjecture is that the period integral over H, this absolute value square of this period integral, gives you this L function, again divided by this normalizing factor, up to some small rational factor that I don't have time to get into. But there is some interesting rational factor here that kind of, when you see an equality with an Euler product, there may be some little rational factor missing that is very interesting. So actually this exact conjecture is due to Ichino and Ikeda, who, you see, again, the left-hand side depends on F. So I said for suitable F, if you want to write down a formula for an arbitrary F, you need to write down this formula. So Ichino and Ikeda conjectured a formula for this integral as an Euler product, of local factors. And then again, this integral, because it's a homogeneous space, has a translation to theta series on this homogeneous space. So again, for example, if you are over a function field, you can take this test function, the characteristic function of the integers, and assuming that all the data are unramified, this integral of Gross and Prasad can be written as an integral over against the theta series. And the Ichino-Ikeda conjecture reformulated as we interpreted it following an idea of Akshay in our joint work. So this is actually Akshay's interpretation of the Ichino-Ikeda local period. It is that the global period, the absolute value square of the global period, or the absolute value square of the L2 norm of the theta series projected to the space of an automorphic representation pi, is this Euler product of Plancherel densities. So again, we see the same thing as with the Rayleigh's inner product formula, where the global inner product is an Euler product of local inner product. So combining the period and the linear paradigms, let's see what we have seen up to this point. We have started with a Hamiltonian space, which was cotangent space of a G variety, or more generally, not of a G variety, of a Lagrangian, which doesn't have to be stable under G. We constructed a unitary representation. We discussed its Plancherel decomposition locally. Now, this Plancherel decomposition does not run over all the unitary representations of the group, of course. In fact, it runs over a very small set of them, usually. So, for example, we saw that in the case of GLN cross GLN, the representations that appear have to be of the form tau tensor its dual. So, in the Langlands philosophy, we want to interpret this as saying that there is a subgroup of the Langlands dual group describing this Plancherel decomposition, and in fact, this is what is happening. To this Hamiltonian space, or to this quantization, we attach a subgroup of the Langlands dual group, which in this case is just GLN, embedded in GLN cross GLN. And this expresses the fact that the representations that can appear on this space cannot be arbitrary, but have to be of the form an irreducible representation of GLN times its dual. So I'm introducing this subgroup that will tell us which representations can appear, both locally and globally. So for example, again, in the theta correspondence, we saw once more that not all representations can appear, but only the representations of the form tau tensor theta tau. So in this example, where the group is SON or SO2n times SP2n, to the Hamiltonian space, we attach a dual group, which is just SO2n embedded diagonally, so to speak, inside of the dual group of G. And this embedding expresses the theta lift. So it is known that this subgroup encodes the Langlands parameters of a representation and its theta lift. And in another example, we took our group G to be SO2n times SO2n plus 1, and our space X was just the group modulo the diagonal copy of SO2n. So here we actually will have all L packets appearing. This is the context of the local GGP conjecture proven by Valfruzet and Moglen in that case, and by Bézat-Plessis and other people in variance, unitary variance. So in that case, all L packets will appear, and therefore the dual group of the cotangent space of X, or the dual group of X itself, if you want, is going to be the entire dual group. And then what else did we see? We saw that the relative trace formula, this pairing of the theta series with itself projected to a representation, And the Ichino-Ikeda conjecture combined tell us that this pairing should be, this is the period pairing. This should be up to a small rational factor equal to an Euler product of the local pairings that we got from the local Plancherel formula.
Yiannis?
Yes.
So there's a question from Jace.
Yes, of course.
Is there an example besides the Weil representation where the symplectic space is not the cotangent space of a spherical variety?
Yes, and I will, so the general case, as I will explain, is a mixture of the two. So you could have the Weil representation on a subgroup, and you could, on a spherical subgroup, and induce it up to the group. So that's a mixture of the Weil representation and the spherical case. So, but I will discuss what the general form is in a moment. So let's see other types of periods like that. One of them is the Whittaker case. So here we take the unipotent radical of a Borel subgroup, we fix a generic additive character. So for GLN, that means like taking the entries above the diagonal and just summing them up. And the differential of this additive character is an element in the dual Lie algebra of N, but I will actually choose an nilpotent lift of that, so I will think of it as an element in the dual Lie algebra of G. And let's compose now this character with a character of the Adele class group, a complex multiplicative character of the Adele class group, and call it Psi. So here we have, first of all, a Hamiltonian space, which is the so-called twisted symplectic reduction of the cotangent space of G by this character of the unipotent group. Explicitly what this space is, it's a symplectic space which as a G space is just you know, if you were just interested in the cotangent space of G mod n, you would just induce n perp up to G. You would just take the contracted product of n perp and G. But now you're not inducing n perp, but you are shifting it by this F. So this is a Hamiltonian space. By the way, this notation here just means contracted product. So I just divide the product diagonally by the action of n. This Hamiltonian space quantizes to the Whittaker model. So we declare the quantization of this Hamiltonian space to be the Whittaker model, the space of functions on G mod on G which vary by this character of n. And its theta series is the well-known Poincaré series, very classical object in number theory. And then the conjectural formula for the projection of this theta series to the space of an automorphic representation has again this form, an L function, which in this case is trivial, divided by the adjoint L function at 1, times a small rational character that we didn't see in the case of GLN, but it exists for other groups. And this formula is conjectural, but is known in some cases, especially by very deep work of Erez Lapid and Zhengyu Mao for the metaplectic groups. So this is a hard formula to prove in general. And the Whittaker case is a case, so let me invoke now the moment map. So remember, all these Hamiltonian spaces come with a moment map to G star, and the Whittaker case is the case where the image of the moment map does not include 0, but it includes another nilpotent orbit. So the smallest nilpotent orbit in the image of the moment map is going to be the orbit of this element F. And now I will tell you what is the general Hamiltonian space that we're considering. It seems, we're not entirely sure, but it seems that we have a good class of Hamiltonian spaces described by the assumptions that I formulated before, and they all turn out to have a very nice structure. Namely, they are comprised of three pieces of data. So let me not go into details, but let me just say that there are three basic pieces of data building these Hamiltonian spaces. One is a subgroup H. One is the subgroup H. The other piece of data is a symplectic representation of H. That's the veil representation piece. So H is kind of giving you the spherical variety type of situation. S is giving you the Hamiltonian space. And then possibly, like in the Whittaker case, you have some unipotent group and a character of that unipotent group. So these data together build a Hamiltonian space. So the situation with the unipotent group gets a little bit more complicated in general. But I think it's going to be, maybe in the interest of time, I will skip that. I will just say that in this, there's a slight generalization of the Whittaker character that I will not get into in detail. And that gives you other types of examples studied by Gann-Gross-Prasad. So these are included in the conjectures of Gann-Gross-Prasad, where what happens is, instead of inducing a character from a unipotent group, this unipotent group has a Heisenberg type quotient. And then you're inducing the veil representation from this unipotent group. So those examples are also contained in the paradigm of quantization that we're studying. But I think if you have seen them before, you know them. If you haven't seen them before, I don't think that this talk is the best place to learn about them. Okay, so these were the examples. Now, let me summarize what we have seen and give you a trailer to the upcoming talks by David and Akshay. So we have seen that general multiplicity-free smooth affine Hamiltonian spaces with some extra assumptions that I mentioned, they are a combination of symplectic vector spaces and twisted cotangent spaces of spherical varieties. And they admit quantizations covering a broad range of periods that we encounter in the theory of automorphic forms. The quantization consists of a local unitary representation and a global theta series, which lives on the space of automorphic functions in G. And it depends on the choice of vectors in the local representations, but over function fields, we actually have a canonical choice of vectors at every place. Conjecturally, the Plancherel decomposition of the local unitary representation entails Langlands parameters from a smaller dual group, not the entire dual group. It could be the entire dual group, but in general, it's going to be Langlands parameters coming from the smaller dual group. So if you write down the local Plancherel formula, it's going to be in terms of the unitary dual of a different group. And conjecturally, again, the components of the spectral decomposition of the theta series with itself, which we call the relative trace formula, the spectral decomposition of the relative trace formula conjecturally admits an Euler product. And the Euler product, sorry, I'm missing the pi here. So on the left-hand side here, there should be a pi. This is just the spectral decomposition of the relative trace formula. The component associated to an automorphic representation pi should be a product up to small rational factor of the local Plancherel densities that we get. And finally, somehow these local factors turn out to be local L factors, and you will mostly hear about this in the other two talks. I'm focusing more on the automorphic side. So what we will see is that on the spectral side, on the side of Langlands parameters, there's a similar Hamiltonian space explaining this phenomena. And let me just give you a quick spoiler. the Hamiltonian space will again consist of the same type of data. There will be a symplectic space, there will be a group H, but the H now is just the dual group of our spherical variety, or or of our Hamiltonian space M. So maybe I should have written here G check sub M. So it's going to be the dual group of the symplectic space M, together with a unitary part that I will explain in a moment, with a unipotent part, sorry, that I will explain in a moment. So again, the data are a symplectic representation. This I will not explain actually today, where this comes from. The dual group describing the spectrum of the local quantization, and then some unipotent piece with a character. I want to tell you a little bit about where this unipotent piece will come from. It will come from a certain SL2 triple. So the SL2 triple giving rise to this unipotent piece, the Whittaker type thing, is one canonically associated to the original space M on the G side, as follows. Up to now I have been stripping it up under the rug. I mentioned that there will be certain Langlands parameters determining the decomposition of the unitary representations, but actually they're not Langlands parameters in general, they're Arthur parameters. So for example, if M is a point, if we consider the trivial case, then the quantization is just the trivial representation, and the dual group is just the trivial group. But we know that the trivial representation of G doesn't have trivial Langlands parameter. What it has is it has an Arthur parameter, which is trivial on its Galois group part, but it also has an additional SL2 triple associated to it, and it's a principal SL2. So the trivial representation corresponds to a principal SL2, and this principal SL2 on the dual side will help us build the unipotent data that we need. And the unipotent data that we need are going to be the unipotent data of the Whittaker space. So we will see that the dual of the trivial period on G is the Whittaker period on G check. Because when we build out our Hamiltonian space out of data of our original space M, and in this case the space was a point, we end up with the Whittaker, the cotangent space of the Whittaker model. And moreover, spoiler again, we will see that this duality is involutive. So the dual of the Whittaker period is the Whittaker of G is the Whittaker period of G check. But also, sorry, this should include an extra line saying that the dual of the Whittaker period of G check of G is the trivial period of G check. So this is the end of my spoiler. And I'm supposed to talk for 75 minutes, I think, right? So this is until past. Is that right, Sogu?
Well, I guess you got 12 minutes.
Yes, okay, good, perfect. Are there any questions at this point?
Not on the on YouTube, but yeah, I have a quick question.
Okay.
So, I mean, a traditional way to think of G-check is, I mean, the G-check is over some algebraically closed field, whereas G is over some number field. So when you say that this is involutive, somehow now we're putting them on an equal footing, or?
Yeah, well, I have two answers. The first is that G-check doesn't necessarily have to be over an algebraically closed field. For example, there are several statements that you can make rationally or even integrally. Yes. With G-check, or maybe a slight variant of that, right? Instead of the L group, the so-called C group. So, for example, geometric Satake can use arbitrary coefficients. So the field of definition or the ring of definition of G check is going to depend on the kind of coefficients that you're using on the automorphic side. Yeah, but on the other hand, yeah, in some sense, I'm formally switching them now. The situation can be made more symmetric if you work in a geometric setting, in the setting of geometric Lagrange, and just you can have complex coefficients on both sides. And I'm sure that David Benzvi will just talk about this setting which is the most relevant one to physics, where both groups are complex groups on both sides. Yeah, but yeah, I would say that there's nothing rigorous about switching them here. Really, as you're pointing out, whatever the fields of definition are, they are a priori unrelated. Yeah. Okay, so the last thing I want to comment on is just to prepare the ground for a more geometric version of our conjectures and of this setup. So to formulate, so up to this point, I have just mentioned and reformulated results and conjectures that were known already, either from Gan Gross Prasad, Ichino Ikeda, or my previous work with Akshi, but just repackage them in a way that makes the Hamiltonian space appear as a fundamental concept. But we can actually formulate some conjectures that are new in a geometric setting. And moreover, these conjectures will give you some conceptual and interpretation of the number theoretic conjectures that you have seen before. So the kind of conjectures that we want to formulate address the following questions. The local question is, what does the Plancherel formula have to do with L functions? And the global question is, what do period integrals have to do with L functions? So in order to formulate these conjectures, we will have to talk about geometric versions of periods and quantizations. So here's the geometric version of the local story. So now we're going to take F to be the algebraic closure of a finite field. F will be a Laurent series over this field, and O will be Taylor series over this field. And for an affine variety X, we will think of the F points of X as bold F points of its loop space. And we're going to think of the O points of X as bold F points of its arc space. So this is giving some scheme or end scheme structures to the points of F and O points, so that we can do some geometry. And now we will consider sheaves on this space. And when I say sheaves on this space, choose any version of the constructible category of sheaves that you like at this point. I'm going to be relatively vague. So we would consider Eladic sheaves, or if you actually want to change your base field, and instead of taking the algebraic closure of FQ, you would like to take the complex numbers as your base field, we could work with D modules. In any case, sheaves on this space will mean L plus G equivariant sheaves on the loop space of X. And it will be, and also this is by definition a DG category. It's not, it's just, you should think of complexes of sheaves, okay? Everything that I will say will be about derived categories or DG categories. So when I say home, I mean X. I mean home and derived home. Okay, so everything from the beginning will be in the derived setting. And little k will be a coefficient field in characteristic 0, depending on your category of sheaves. The sheaf function dictionary in the L-adic setting allows us to translate between sheaves on this space and GO invariant functions on X of F. Okay? And moreover, it allows us to translate homomorphisms or X between the sheaves into inner products. Through this very simple formula, suppose that you want to calculate the inner product of two functions on the FQ points of some variety. If these functions arise as traces of Frobenius through the sheaf function dictionary, then you can calculate this inner product by applying the trace of Frobenius to the homomorphisms between those two sheaves. And again, I stress again that homomorphisms means ext, means derived homomorphisms. So now this simple formula tells us that, going back to our spaces, if we want to characterize the Plancherel density of, let's say, the constant function on X of O, then we would be asking the question of what are the self-homes of the constant sheaf on the arc space of, typo here it should be X. Our goal is to understand the inner product of the characteristic function of X of O with itself. Okay, so this is a typo here. It should be the constant sheaf on the arc space of X, so that when you take trace of Frobenius, you're going to get the characteristic function of X of O, which was our basic object. So the question of relations between Plancherel formula and L functions becomes the question of describing the endomorphisms of this constant sheaf, where here it should be L plus X, in terms of something that has to do with the L function. And in the talk of David Ben-Zvi, you will hear something about the endomorphisms of this basic object. And then what is the global story? What is the geometric version of the global story? A geometric version of the global story is the so-called, what we call the period sheaf. The period sheaf is the geometric version of this theta series that we were considering before. So let me just recall from the Iwasawa-Tate case, our space was just the affine line. The group was just the multiplicative group. Our basic function was the product over all places of the characteristic function of the integers. And this gave us a theta series on the Picard group, which counted the number of sections of each line bundle. So the value of the theta series at the line bundle is the number of sections. Let me describe this same formula geometrically. The Picard group is maps from the curve to the classifying space of the group. Okay, so when I say it classifies line bundles, it's the same as saying that it classifies GM bundles, and that's the same as saying that it classifies maps from the curve to the classifying space of GM. Now let me define peak X of C, so a labeled like a decorated peak of C, which will be maps from the curve to A1 mod G. So this is the stack which classifies pairs consisting of a line bundle together with a section from the curve to this line bundle. Okay, and obviously you have a map between them, which is a forgetful map, and I denote it by pi. Then the theta series that we just saw is just calculating the trace of Frobenius on the push forward of the constant sheaf under this map from the decorated peak to the peak. And this is what we call the period sheaf in general, in this case. And for a general G space, we will define the period sheaf in exactly the same way. So we start with G bundles on the curve. These are maps from the curve to the classifying space of G. And we are asking, we define a space over it, which is classifying G bundles together with a twisted section, together with a section into X, with a map into X. Or, yeah. And then the theta series associated to this space X is the trace of Frobenius on the push forward of the constant sheaf. Here I'm assuming that the space X is G-stable, but if you are in the linear case with a Lagrangian, where X is just a Lagrangian on a symplectic G space M, this construction has been generalized in papers of Lysenko. And again, like I mentioned, I'm skipping various twists that one needs to incorporate here. And this is what you will see in papers of Lysenko, or what you see here in this example. This is just the geometric version of the theta series, is the geometric version of our global quantization. So what questions can one ask on the period sheaf that will be addressed to some extent in the lecture of Akshay? First of all, the first question is to evaluate the pairing of the theta sheaf with Hecke eigensheaves. That's the geometric version of, so home from one sheaf to the other is the geometric version of the period integral against an automorphic form. Or the analog of the relative trace formula question, evaluate just homes from theta to itself. So derived endomorphisms of the period sheaf, and that roughly corresponds to the relative trace formula inner product of the theta sheaf, of the theta series with itself. Okay, so these are the questions that I left the hard questions to my collaborators, and who will explain to you how to conjecturally answer these questions by invoking the Hamiltonian G-check space, the Hamiltonian space on the dual side, in a way that recovers the relevant L functions. And I will stop here. Kamsahamnida.
Thank you very much for your enlightening lecture. So it's time for questions. Also, everyone is welcome to ask questions on YouTube. So meanwhile, maybe I'll ask one question, if I may. So so you said that basically the local Planck-Shuttle density is like a local L function, but then I guess you were suggesting that there's a geometric version or geometrization of this. Mm-hmm. But then I guess, but in practice, oftentimes this comes down to some elementary computation with, kind of some sort of infinite series. So I don't know, like whether there is an easier way and a kind of a fancier way, or actually this is the right way. I mean, maybe the kind of geometric point is the right way.
Well, I mean, it depends on what you want to achieve. For many purposes, just doing the explicit calculation is just fine. But somehow I think it's very unsatisfactory that the L function comes out of the blue and you don't understand why an L function should be appearing there. Like this is, we're talking about, these methods of representing L functions are the basis of all of number theory. Every time you get your hands on an L function, you rely on one of these methods. So I find it very unsatisfactory that in the end it boils down to a calculation that looks like a miracle. So we're trying to explain this miracle, and I think that whenever you explain a miracle, there's other good things coming out of that. I should also mention that doing this calculation is not always a piece of cake, especially if we were to generalize this story to singular varieties where the basic function is not the constant function on the integral points anymore, but it is some function coming from intersection cohomology. So that takes us in a different direction, but there is recent work of mine with Jonathan Wang, which is really complicated, and it took some amazing insights by Jonathan in order to be able to compute these Plancherel densities in terms of L functions in those cases.
Yeah, that's an excellent answer to a dumb question. Thank you.
It's not dumb. It's not, of course not.
Yeah, there's another question by Mr. Tashov on YouTube.
Is that the Mr. Tash I know?
Well, yeah, the question is, does the duality M between M and M dual extend the duality between G and G dual? If yes, is there some well-defined category like reductive groups in which it is defined?
Yeah, so I have a positive and a negative answer to that, and I'll give both. So the negative answer is that we start with G and G dual, and then we consider, and the duality of M and M check is going to be a duality of different objects. These are spaces, Hamiltonian spaces for those groups. I think this will be understood better in the lecture of David, where the group and its dual group are giving you a certain hierarchy of theories according to the paradigm of quantum field theory. You have a theory for the local group, you have for the local case, you have a theory for the global case, you have a theory for the geometric case, and then the Hamiltonian space is giving you an object in this theory. So in that sense, this duality is a duality of certain objects. David will explain to you that they understood as boundary conditions in quantum field theory. Duality of certain objects inside of some categories attached to G and G dual. That's my negative answer, and it's the more serious one. The positive answer is that, on the other hand, you can view the group itself as a symmetric space, as a spherical variety for two copies of the group. So in that sense, the group is just a special case of the more general story. Yeah, so that's the answer.
Maybe if I can add a word to your,
Perfect.
There's a duality if you don't try to get M and M check themselves directly, but if you're trying to get rid of the group and you want just to say something about there's something called symplectic duality or three-dimensional mirror symmetry, which is a relation between just symplectic varieties and dual symplectic, just a duality in symplectic varieties. This won't recover n and n check themselves. On one side, you have to take the kind of quotient by GIT quotient by the group. On the other side, you have to do something like a Whittaker reduction. But so in any case, given the duality we're talking about between n and n check, there's some kind of Hamiltonian reduction you can do on both sides, and you get two symplectic varieties, which you could formulate are dual in a way that doesn't mention any groups. So this kind of refinement of that symplectic duality.
Well, thank you. Well, are there further questions? Yeah, actually, I have another question. So you mentioned that this well, inner product period in the context of relative trace formula, but then is there some sort of geometric viewpoint on the geometric side of the relative trace formula?
Well, the geometric version of the relative trace formula has to do with decomposing these endomorphisms of the period shift. So it's, in principle, it's computing in principle, if you apply, if you could apply trace of Frobenius to that, you would get the inner product of the relative trace formula.
So are we computing this endomorphisms in two different ways in some sense?
Well, yeah, on one hand, okay, so the geometric side of the relative trace formula does not appear anywhere here, what is called the geometric side. We don't decompose in terms of orbital integrals. This, I mean, I guess if you were to actually write down what this inner product means, then you could do it. But anyway, there's nothing new that we have to offer in this direction. But the fact that on the spectral side, you get L functions, at least, you know, at some not completely rigorous level, because you have to be careful about applying trace of Frobenius on certain objects where I'm not sure everything is yet well defined, but yeah, so it will come out of our conjectures, at least at a formal level, that the spectral decomposition of the relative trace formula is in terms of L functions.
Well, yeah, thank you.
Same as with the Plancherel formula locally. I mean, you have an interpretation of these pairings on the G-check side, and then if you were to apply a trace of Frobenius on that, it would just amount to an integral over L functions.
Yeah. Thank you. I'm more than happy, and I should stop harassing you with more questions. And we're only 2 minutes away from the next talk. So I'd like to thank you again for a wonderful talk.
Thank you.
Thank you, Yiannis, for beautiful talk.
And yeah, well, in 2 minutes, we'll hear from Dohoon Choi.
Okay, welcome back to last talk of today. Professor Dohoon Choi from Korea University will present his talk. He is originally from BS, bachelor degree and PhD at PostDoc. He's been visiting professor at KIAS and the Kyushu University. So now let us welcome him.
Yeah, thank the introduction and thank you for the invitation in this workshop. Yeah, the subject of my talk is related to automorphic forms, but yeah, it is not so closely related to the periods of automorphic forms. I'm sorry about that. Anyway, today I will talk about this question. Let F be a totally real field. Let A sub F be the other ring of F. Yeah, this is the question. Is there a finite field, finite set W of finite places of F such that a cohomological hospital automorphic representation of GLN of F with a fixed level is uniquely determined by its local representation at places in W? If the answer to this question is yes, then we have a finite set W such that for any two cohomological hospital automorphic representation. Yeah.
But the weight varies, or what?
Yeah, well, weights varies. Yeah, in this case, weight is not fixed, but its level is fixed. Yeah. Okay. Yeah. Oh, yeah. This question is related to a classical result to Dirichlet characters. Let me give you some history about this question. Let chi be a non-trivial primitive Dirichlet character modulo of prime q, and sub chi be the least positive integer n relatively prime to q such that n of chi of n is 1. I'm sorry, chi of n is not 1. Yeah, then Vinogradov conjectured that if chi is a Lambda symbol, then n sub chi is big of q to the epsilon for any positive is epsilon. Yeah, his conjecture asserts that the least quadratic non-residue modulo of prime q is big of q to the epsilon for any positive epsilon. Yeah, this conjecture was investigated by Univ. Yeah, he introduced the classical large sieve method in 1941, and he used it to prove Vinogradov's conjecture under the generalized Riemann hypothesis. Yeah, this bounds was improved by Uncanny, yeah, under also assuming generalized Riemann hypothesis. For general Dirichlet characters chi, Uncanny improved this bound to big of log scale under the generalized Riemann hypothesis. Yeah, in fact, this result gives an answer to the question, what is the smallest positive integer n sub q, such that chi is uniquely determined by its value of chi of p for primes p less than or equal to n sub q. Yeah, you can easily see this by considering a dirichlet character times the inverse of another dirichlet character. The only extension of this question to automorphic representations were investigated in several aspects in several mathematicians such as Bruni, Duke and Kowalski, and Kortfeld and Hofstein, Moreno, Serre, and so on. For example, Bruni and Kortfeld and Hofstein, Moreno, considered the number of local representations uniquely determining a unitary Cospedal automorphic representation. Duke and Kowalski and Serre, in another view, they considered this question. They studied multiplicities of automorphic representations with the same local representations at some places. First, let me talk about the extension of this question to automorphic representations corresponding to U-forms on SL2Z. Let F1 and F2 be distinct U-forms on SL2Z such that F1 and F2 are normalized. Here normalized means their first Fourier coefficients are 1. Ki be the weight of Fi. For prime P, lambda sub Fi of P, the Hecke eigenvalue of Fy for the piece Hecke operator Tp. Let me note that if F1 and F2 have the same eigenvalue for the piece Hecke operators, then the local representations of the Cospedal automorphic representations corresponding to F1 and F2 at P are isomorphic. So let me consider the following numbers. Let n of F1 and F2 be the smallest prime such that the eigenvalue over P to the 1 over 2 times K minus 1. And this value is called normalized eigenvalue. So n of F1 and F2 be the smallest prime such that their normalized eigenvalue are different at P. Assuming the generalized Riemann hypothesis for any F1 and F2, we assume that F1 and F2 are normalized U-forms on SL2Z. In this case, n of F1 and F2 is bigger of log scale of the maximum of K1 and K2. In fact, this is implied by the general bound for Cospedal, unitary Cospedal automorphic representation, under assuming the generalized Riemann hypothesis. Without assuming, we have n of F1 and F2 is bigger of the scale of the maximum of K1 and K2. By assuming another conjecture, in fact, we can improve this bound. The conjecture is called Maedad's conjecture. Before giving you the conjecture, let me pick some notations. Let S of U of SL2Z be the space of cusp forms of weight U on SL2Z, and E sub PU be the Galois closure of the splitting field of the characteristic polynomial of TP on this this space of cusp-forms. So, yeah, this field, yeah, as you know, the characteristic TP is act on the space of cusp-forms. So this characteristic polynomial is depends on this space. So, yeah, this field is depend on P and U. Yeah, the conjecture proposed by Maeda asserts that for each prime P and for each when U, the Galois group of EPU over Q is isomorphic to symmetric group whose order is equal to the dimension of the space of cusp-form of weight U. Yeah, this conjecture compound for many cases numerically. So, yeah. And this conjecture immediately implies that the characteristic polynomial of TP on the space of cusp-form of when U is irreducible over Q. So, assuming Maeda's conjecture, we have this. Yeah, if K1 and K2 are the same, yeah, the weights of two U-forms are the same, then their eigenvalues for the Hecke operator T2 are distinct roots of the characteristic polynomial of T2, because the characteristic polynomial of T2 is irreducible. Yeah, if these dimensions are different, then the characteristic polynomials of T2 have different degrees. So the second eigenvalues of F1 and F2 are different. So we have this bound. Under this assumption, n of pi F1 and F2 is 2. Yeah, motivated by this observation, I studied the following theorem. Yeah, in this theorem, we don't assume any conjecture. Assume that F1 and F2 are normalized U-forms of weight K1 and K2 on SL2Z, respectively, if they have the same eigenvalues for the second Hecke operator and seventh Hecke operator, then these two Hecke normalized U-forms are the same. In other words, the normalized U-forms on SL2Z are uniquely determined by its the second normalized Hecke eigenvalue and seventh normalized Hecke eigenvalue. So, yeah, this theorem improves the known bound, the log scale bound. Yeah, obviously, this theorem implies that if the levels of distinct U-forms F1 and F2 are 1, then n of F1 and F2 are uniformly bounded 7. In fact, the existence of a uniform bound for n of F1 and F2 can be extended to cohomological cuspidal automorphic representation of CLN, such that their levels are bounded by a fixed constant. Yeah, before considering this situation, let me give you some known results for general unitary cuspidal automorphic representations. Let F be a number field. A sub P will be the other ring of F. Yeah. A sub F and small f denotes the finite parts of the other ring of F. Let O be be the ring of integers in FB, let pi and mu are distinct cospidal autopy representation of GLN AF with the same central characters. This autopy representation pi and mu are decomposed into restricted tensor product of their local representation pi b and mu b. Here pi b, it denotes the local representation of pi at the place b. Let n of pi and mu be the smallest integer mb. As in the previous section, we define n of pi and mu in this way. This is the smallest integer n of b such that pi b is not isomorphic to mu b, and pi and mu are unlamited at this place. Here n of b denotes the absolute norm of b. In this case, we consider b as the prime ideal of the ring of integer in F corresponding to the place b. Then, strong multiplicity 1 theorem implies that n of pi mu is always finite number. So it may be a natural question to estimate this number. Some upper bounds for this number was given in terms of the analytic conductors of pi and mu. Assume that the analytic conductors of pi and mu are less than large Q, and further assume that pi and mu are unitary. Moreno, n is 2, Brumley for general n, proved that n of pi mu is big over q to the a for some a, depending only on n. In fact, Moreno obtained some upper bound for n of pi and mu for general n, but n is larger than 2, his bound is exponential type. This is improved by Brumley. As in Dirichlet characters, assuming generalized Riemann hypothesis, n of pi mu is bigger over log scale. So, in this talk, let me talk about to improve this bound under the assumption on our autopic representations that are cohomological and they have a fixed level. Now let me give you what is a cohomological autopic representation. Let pi be a cospidal autopic representation of GLN AF. For its infinite place B, pi b can be considered as GK module. This is denoted by B sub pi b, where GB is the complexification of the Lie algebra of GLN of FB, and KB is a maximal compact subgroup of GLN of B. Then we say pi is cohomological if for each infinite price B, there exists an algebraic representation B sub lambda of GLN of FB such that this ith GK module GK this i's GK module homology is non-trivial for some non-negative integer I. So this tensor product is a representation of GLN of FB. So this representation is corresponding to some GK module. This denotes its i's cohomology. Now we assume that pi and mu are cohomological. The analytic conductor of cohomological automorphic representation, pi depends on the level and the weight of pi. So very roughly speaking, the weight is depending on the finite local representations of pi. The weight of pi is depend on the local representation of pi at infinite places. For example, pi is correspond to a U-forms where k on gamma 0m. Then the analytic conductor of pi is n times k squared. So let me point this. If we, although we pick a level, the analytic conductor of pi is unbounded. Now let me give you the definition of levels and weights of a cohomological automorphic representation. For positive integer n, let k of m denote an open subgroup of GLN of A and GLN of the finite part of the AF. K of m is defined by the product of an open subgroup of GLN OB. If B divides P doesn't divide n, then the subgroup is equal to GLN OB. If B divides n, then the subgroup consists of G in GLN OB, and that is congruent to identity matrix modulo B to the MB. Here MB denotes the valuation of M at B. On automorphic representation, pi of GLN F is said to have level n if n is the smallest positive integer such that the finite part of pi has a non-zero k of n, the fixed vector. Now I gave you the definition of the level of automorphic representation. Next, let me give you the definition of the weight of a cohomological automorphic representation. Let omega be an algebraically closed field of characteristic 0. Let g to the n to the home of fc plus be the set of tuples A, consisting of A tau I. A tau I is in the this product set, is such that if we pick tau, then tau I is decreasing as I is increasing. For I, let xi be the tensor product of A, xi, A, tau, where xi A tau is the irreducible representation of GLN of the highest weight A tau. We say A is the weight of pi if pi infinite has the same infinite character as xi A pole. Yeah, we assume that the levels of pi and mu are bounded by a fixed constant. Yeah, in this case, up to my best knowledge, the known bounds for general n are given by the previous result. So in other words, the n of pi and mu is big of polynomial. Yeah, if we assume the generalized Riemann hypothesis, n of pi is big of log scale. Yeah, it's in particular when pi and mu are correspond to f1 and f2, that are normalized U forms, normalized distinct U forms on gamma 0 n, the exponent a in this bound was further studied. Yeah, here we fix n, that ki be the weight of fi. Yeah, Sengupta obtained that n of f1, f2 is big of the maximum of k1 and k2 to the 2 plus epsilon. Conan remove epsilon in this bound. So in the parallel, in the next theorem, I proved this bound, improved this bound. F be a totally real field, let pi and mu be distinct cospeidal automorphic representation of GLN of AF, such that pi and mu are homological. We assume that the levels of pi and mu are bounded by a fixed constant n. Then there exists a constant Cn, independent of pi and mu, such that for every pair pi and mu, n of pi mu is less than or equal to Cn. So under this assumption, the n of pi and mu is uniformly bounded to this constant Cn. So now let me give you some remark on this theorem. On explicit Cn can be given in terms of dimension of this topological cohomology, where xk denotes a local symmetric space defined by this quotient. Here, K infinite denotes the maximal compact subgroup GLN of F times F tensor R. On explicit Cn can be obtained in the following way. To get an upper bound Cn, one can use the distance method and effective Cherev-Taleb theorem by Lagaris, Montgomery, and Oderisk. Then, an upper bound for Cn is given by a formula involving this number is denoted by n of x, of isomorphism classes of number fields whose absolute discriminants are less than x. We use the upper bound by Ehrenberg and Pancartesi for n of x so that we get an explicit Cn. This is another remark on the case when the level weight is fixed. It is obvious that there is no constancy for every distinct pi and mu with a fixed weight. N of pi and mu is less than or equal to C. For example, under assuming generalized Riemann hypothesis, Montgomery proved that for some fixed positive constant C, if there are infinitely many primes Q such that for all non-negative integers m, that is less than or equal to C times log Q times log Q and quadratic residues modulo Q. If we, in this theorem, if we replace the bound C times log Q times log Q with C times log Q times log Q, then this is true without assuming generalized Riemann hypothesis. This is proved by Graham and Ringrose. Let me remark on the multiplicities of Cox-Peter automotive representation of GL and with the same local representation as some places. Really proved that if alpha is a positive real number, then for all positive integer m, there are at most C alpha real Dirichlet character chi modulo Q such that Q is less than or equal to m, and chi of n is 1 for all positive integer n, that is less than or equal to n to the alpha. This was extended to by Duke and Kowalski to automotive representation with a fixed level, in particular, especially elliptic curves defined over Q. This case was also considered by Serre. Let M L of X be the maximum number of isogenic classes of semi-stable elliptic curves E over Q, satisfying these two conditions. The conductors of E are less than or equal to X. E has a fixed number of FP points at primes P, that is less than or equal to Cx. Duke and Kowalski proved that if C of X is log to the alpha for any positive alpha larger than 1, then for every positive epsilon, M L of X is big of X to the 8 of alpha plus epsilon.
Excuse me, may I interrupt?
Yes.
So the James asked the following question. What if you fix a prime and conductor and consider a tower where only the level go to infinity?
In the next remark, I will consider the case.
Yes.
So in this view, our main theorem can be restated. Our theorem can be applied to study an analog of this to a set H consisting of cohomological automotive representations pi of GLN with a fixed level. Then, in this case, we have if H of X is a function from the set of positive real numbers to itself, such that its limit is infinite as X goes to infinite, then for any sufficiently large X, the maximum of the number of pi in H having fixed local representation pi b for n of b that is less than or equal to pi of X is 1. Maybe this is an answer to the question of gets. And we assume that L be a prime larger than or equal to 3, for positive integer n, let S nu of n be the set of normalized U-forms on comma 1n. Let S nu of n L infinite be the set of U-forms whose labels are the product of n and any power of a prime L. And now we assume n L are fixed. Then there exists a constant C and L such that for every pair F1 and F2, n over F1 and F2 is less than or equal to C and L. In the proof of our theorem, we consider the reduction of Galois representations associated with a cohomological automorphic representation. In this case, Galois representation associated with U-forms. Let me note that the modular model Galois representations arise from a U-form whose level is relatively prime to L. So, by using this, we can consider only model representations coming from U-forms whose level is n. So, we get this theorem. Let me give you another point of this theorem. To consider the normalized eigenvalues of U-forms, we have to normalize the determinant of Galois representations associated with U-forms. But if the weights of two U-forms have different parities, we cannot do this. In this case, we consider the symmetric scale of these two Galois representations and comparing their Hot-state weight, we can solve this problem. So, eventually we get this part. This is a final remark on our theorem.
Can I interrupt you? So I guess the maybe question is about the C and L when you let L go to infinity. So in other words, can you have some idea this constant in terms of L?
Maybe in his question he's fixed it. In this case, L is fixed, the power of goes to infinite.
Okay, thanks. Go on. Thank you.
Thank you. If there is no question, let me give you a brief outline of a very brief outline of the proof. The known bounds for n of pi and mu are based on the one of the following ingredients. One is analytic properties of the ranking set of L functions to automorphic representation of ZLM. The other one is the Riemann-Roch theorem for modular curve of a field. For example, Moreno and Bruni obtained their bound by using differentiates two kinds of Rankine-Serbov L function. Yeah, one is the Rankine-Serbov L function of two distinct hospital automorphic representations, and the other one is the Rankine-Serbov L function of the two same automorphic representations. Yeah, these two Rankine-Serbov L functions have different analytic behavior. By using this, they prove the polynomial bound for n of pi and mu in terms of analytic conductors. For example, for Riemann-Roch theorem, if the weights of F1 and F2, F1 and F2 are U-forms of weight K on SL2Z, then by Riemann-Roch theorem, n of F1 and F2 is less than or equal to K over 12. As I know, these two ingredients are standard method to solve this problem. Contrast to the previous result, we prove our main theorem by using the deformation theory for pseudo representations. I already gave you the definition of these rotations. Let S be the finite set of finite places of F containing all places dividing L times d sub F. Here, d sub F denotes the discriminant of F. So, S contains all places above some prime P is such that P is ramified in F. We further assume that if B in S is above a prime P, then S contains all places above P. Let me note that these assumptions of S is important. Let K be a compact open subgroup of GLN of A, the finite part of F having this form. This K is the product of a subgroup of GLN OB. If P is not in S, the subgroup is GLN OB. P is in S. The subgroup is any compact open subgroup of GLN OB. I also gave you the definition of this locally symmetric space. Assume that F is a totally real field or CM field. Harris-Rand-Taylor-Sloan constructed Arabic Galois representation rho pi associated with a cohomological hospital automorphic representation pi of GLN of F. In fact, the constructions of Galois representations are obtained, developed by many mathematicians, Harris-Taylor, Sin, and Simura, Eichler, and so on. So anyway, in this case was proved by, in this case, the construction was obtained by Harris-Rand-Taylor-Sloan. Their result immediately implied this theorem. Assume that pi is a hospital automorphic representation such that pi is a cohomological, and such that pi sub f has a non-zero k fixed vector. If pi prime is the tensor product of pi and the norm of determinant to the 1 minus n over 2, then there exists a unique semi-simple continuous representation log pi of CFS. CFS denotes the Galois group of the maximal unmagnified extension of F outside S. Such that for all finite places B not in S of F, the Satake parameters of pi prime B are the same as the eigenvalues of rho pi of prob B. Prob B means a Frobenius element of GFS at the place P. Thanks to this theorem, we can consider Galois representations instead of cohomological automorphic representations. To use the deformation theory, we need a finite list of the reduction of Galois representations associated with these cohomological automorphic representations. That is given by the result of Church. The result of Church on the construction of Galois representation associated with mod L to the m cohomology of the locally symmetric spaces for GLN of F implies that if the levels of pi are fixed, then there are only finitely many pseudo representations tau bar. Finite many is important. It's such that for some pi, we assume that pi is a cohomological automorphic representations with a fixed level. For some this pi, rho bar is the trace of the reduction of rho pi. If we assume pi is essentially self-dual, it is rather it is rather obvious by the theory of algebraic automorphic form, but in this case, at least for me, to prove the finiteness of these such pseudo representations, I need the result of Church on model cohomology of the locally symmetric spaces. So the proofs reduced to finding of finite set W, finite places of B of F, such that T sub tau bar is the lifting of tau bar to the pseudo deformation ring of tau bar. Then for any constant CB, there is at most one point in genetic fiber of the pseudo deformation ring of tau bar satisfying these equations for all B. T tau bar of Frobenius B is CB for all V. For remain some minutes, let me give you more details about this. L be a prime, E be a finite field extension of QL. In my talk, F is a number field, E is a local field. And O sub E be the ring of integers in E. Let K be the left field of E. Let C hat denotes category of complete Nestorian local OE algebra with left field K. Let tau bar be a pseudo representation of dimension L. In our proof, we assume that L is larger than M factorial. Instead of, if we use Chenever's Chenevier's determinant theory instead of pseudo-representation theory, maybe you can remove this assumption. Let A be a complete local OE algebra. A pseudo-representation tau is called the lifting of tau bar to A. This is congruent to tau bar modulo MA. We define a functor T sub tau from the category of component Nestorian local OE algebra to the category of sets by this. A goes to this set, the set of liftings of tau bar to A. Then the functors T sub tau is represented by a complete Nestorian local ring. This ring is denoted by RPS sub tau bar. This ring is called the pseudo deformation ring of tau bar. By the classification of the complete Nestorian local ring, we may assume that this pseudo deformation ring is isomorphic to this power series ring. So Xi denotes the generators of this ring. Back to the pseudo deformation ring of tau bar. Let us note that if tau bar is equal to trace of the reduction of rho tau bar. I'm sorry, I have to note current representations. So this is of reduction of rho pi. Then there exists a unique local OE algebra homomorphism tau sub pi from the pseudo deformation ring to some A, such that tau sub pi composed with tau bar is the trace of rho bar, a trace of rho pi. So, to prove this theorem, it is enough to show that there exists a finite set. This set is denoted by W sub tau bar. OCL. OCL is less than or equal to 1. And there is one OE algebra homomorphism pi from the pseudo deformation ring of tau bar to the normal pi of xi is strictly less than 1 for all I, and tau sub pi of t tau bar of provenience B is in the set.
Dohoon?
Yes?
I think maybe connection is not smooth. Can you Stay with your microphone closely.
Sorry, I can't hear you.
You can. Can anyone hear me?
Yeah, maybe my internet has some trouble.
Yeah, because it's
I'm-
coming and going.
Yeah, I'm sorry. Yeah. So, oh, yeah. So, yeah, so, yeah, the theorem is implied by this. So, yeah, to prove this, of the pseudo-deformation ring, we use the Chebyshev tenth theorem. So, yeah. Yeah. I hope to stop here. Thank you for your listening. Thank you.
Can you hear me?
Yes.
Good. So are there any questions or comments? Can you just put your slide for the main theorem? Dohoon?
Yes.
I'd like to ask you if you can put your main theorem on the slide.
Yeah.
Thanks. Okay, are there any questions or comments?
So are you making basically the same argument for modular forms of level 1, or is it a different argument? I mean, when you show that the set n consists of 2 and 7.
Oh. Oh. I'm sorry. Oh.
It's Q&A time, so take it easy.
Yeah, so yeah, maybe my internet has some trouble, so.
So you can, but you can just say that.
Yes, but yeah, sometimes I cannot hear you, so yeah, that is a, yeah, that is a problem.
So Seogu asked the following question.
Yeah.
So does your argument for GLN also apply to the level 1 cost form to show that the set capital N is 2 and 7?
Yeah.
That's his question.
Oh, sorry, can you say again?
Seogu, he cannot see the chat. You have to put it on the YouTube. So you had a level N case, level 1 case, 2 and 7, right?
Oh, yeah, why? Oh, can you hear me? Oh,
Yes. Sogo, can you hear?
Yes.
yes. So, but, yeah, can you chat about your question? I'm sorry, I cannot hear you. Yeah,
I was just asking what you did to prove your result for cost forms.
oh, because of my internet, I'm very hard to understand your speaking. So
maybe later. You don't
yeah. Now I disconnect my internet and try again. Yeah.
Yeah, it seems that the speaker has a problem with internet connection. So probably if there is any comments among the speakers, probably we can discuss. Otherwise, we are ready to close the session. Don, can you hear me?
Yeah. Yeah. Oh.
So I think maybe probably because of your internet connection, probably we can talk later in person.
Yeah. I'm very sorry about this. Yeah.
Yeah. So if there is no further comments, I'd like to close today's session by saying that we had 3 fantastic talks. Although we had a little problem with the internet for the last talk, but still it's a wonderful talk. So I'd like to thank to all speakers today. We will resume, and thank you for all participants staying us until now. We will have 3 more fantastic talks waiting for tomorrow. For tomorrow, we will resume at 8:30 Korean time sharp. So speaker can maybe 10 seconds more, because I like to discuss about the program privately. Thank you very much. So see you tomorrow.